Hello, everyone. Welcome to the problem solving session 4. In this session, we will solve exam questions from spring 2020. And we'll start with the second question, the Verilog question. And yeah, I'll just get started with it. So I hope you can see everything fine here. And the second question, Verilog question, starts with, does the following code result in a sequential circuit or a combinational circuit? Please explain your answer. And yeah, when you look at this code, the first things you probably notice is the input of 4 bits, data input, and an output register named segments. And it's 7 bits large. And in the always statement, we have a sensitivity list of star, which means it will be executed when any of the data that's being read in the essentially read in the always block changes. And here there's a case statement. Inside the case statement, we're looking at the data value. And for only 5 of these values, we have an assignment here for the segment output. And because of this, because not all the left, because we have segments as a left-hand side operand in these statements, and they are not assigned to a value in all cases, this is a sequential circuit. So the answer is sequential. And the reason why that, I'm going to explain a bit more. So data is 4 bits large, but in the case statement, we're only covering 5 of the available 16 different values because data is 16. The data can have 16 values because it's 4 bits. Now, because we don't have an assignment for other values of data here, what this will output as a circuit is some circuit that's going to hold a state for the segment's output. So basically, when the data is 4D5, like basically data encodes the value 5, this statement won't reassign the value of segments, so it needs to remember it. That's why it will essentially end up generating probably a latch in your circuit. Any questions about this one? Okay. Yeah, okay, I'm moving to the next one then. Cool. Yeah. Nice. Yeah, zoom out a bit, and you can still see it, I guess. Yeah. Okay. And the second question is, does the following code result in an output signal which is 0 except for 1 clock cycle in every 3 clock cycles? And if not, please enable this functionality by adding minimal changes and explain your answer. So the module is called divide by 3, and it has 3 inputs, clock, reset, and 2 inputs and 1 output Q. And the question is asking if this Q is 0 except for 1 clock cycle in every 3 clock cycles. So we can look at this line. This is where Q is assigned to its value. And Q will be set essentially to 1 if this statement is true, right? Because we have this equality operator here. Maybe I can zoom in a bit. Okay. So whenever current value is S0, which is here, it's basically 0. Q will be 1. And these S0, S1, and S2, as you can see, the encodings for the state machine, most likely, and the way they declared. And in the always statement, which is triggered on every input, like it's an always at star statement. So it's like where we define our combinational circuit, right? We look at the current value, and depending on its value, we set the next value to either S1, S2, or S0 here. And the default case is S0, but it's not really important because we covered all the cases for current value, but it's because it's 2 bits, we have to cover another value which is not encoded here as S3, for example. So this is, we're just doing that to make sure that this indeed generates a combinational circuit. There's nothing wrong here. But the problem is, you can see that when the current value is S0, we assign it to, like, the Q becomes 1. But current value is only declared here, and there's no assignments to it. So this is supposed to be a state register, but the code that will make it a state register is missing. And to do that, we need to add 2 lines of code, basically. And we need to add a new always block to make sure that the data is registered. The next value is registered to the current value when we want it. So maybe 3 lines. Okay, so this is an always at postage clock. We want this to be triggered with the positive edge of the clock. And a reset signal, because when the circuit is reset, we want the current value to have a valid value. And then inside here, we will have, if reset is high, we're going to assign 0 to the current value. And if it's not, we're going to assign the next value to current value. And what this does is it makes it a proper state machine. And then if you trace the code, you will see that the current value starts with 0, so it will output a 1 when we reset the circuit, basically. When we set the reset signal and the positive and the clock hits, the current value will be 0, so Q will be 1 in the next cycle. And then the next value will be assigned to S1. S1 encodes 1. So the current value, when the clock hits, will become 1. And then it will become 2. And in these 2 cycles, it will output 0, because this statement will end up being 0. And then it will go back to state 0. And when it comes back to state 0, it will output 1 again, and it will continue forever. Okay. Yeah, any questions about this? Yes. I think you can do it for this question, as long as you set it to, yeah, you can set it to anything. Because basically, if you set it to, I was going to say, if you set it to S3, then it might not work, but this default case here will cover that. So next value will be 0 in that case. And then the current value will become 0 in the next cycle. And if you set it to anything that's already listed here, then it's just going to continue the way it's supposed to, according to the state machine. Yeah. I think that would be correct also. Yeah. Yeah, it will be triggered. The block will be triggered whenever the reset signal changes. I don't think it's going to change the behavior for this question, basically, for this code. Yeah, but then you have this if reset that prevents it from executing. Okay. If there's nothing else, moving to the next one. So it's C. Zoom out a bit again. Okay. So again, we're looking at the Verilog code. This code implements a circuit, and we initialize all inputs and registers of the circuit to 0. That's what is already being done in the code. And we apply the following changes to the input signals in 2 steps. What are the values of out and temp this register after each step. And in step 1, okay, maybe before I talk about the steps, I talk about what the code is doing. So it has, this time it has 4 inputs, 1-bit inputs, select A, B, C, and out. 1-bit output, out. And inside the module, we define a register that's assigned to 0. And we have an always block here that's triggered when the select signal or cell signal is, and it switches value. So there is like an if statement here and an else statement that complements it. I think there's like a problem in this code. So there should be begin and end statements here. Basically to make sure that those 2 lines of code remain in the correct place, like in the if statement and then the else statement. Yeah, and then in these if and else statements, we have assignments to temp and out. So in step 1, select signal will change to 1. So what will happen is this always block will be triggered because cell changed this value from 0 to 1. It was 0 in the beginning because the question says we initialize all inputs and registers of the circuit to 0. Now we change it to 1. And the always block will again get triggered, as I said. And then the block that will be executed is the if block. What happens is temp gets assigned to the A and B. A and B is not, or in like the inverted value of A and B. And that's going to be, because A and B are 0, this is going to be 1. So in step 1, temp, well, one side, temp will be 1. Okay. And the out is the XOR of temp and C. But because these are non-blocking assignments, the value of the new value of temp, which is 1, is visible only at the end of this always block. So this line of code will still, or this statement will still operate on the earlier value of temp, which is 0. Is that correct? Yeah, because temp is in the beginning 0, it will operate on that value of temp, which is 0, and then it will XOR that with C, which is also 0, and 0 XOR 0 is 0, so out will be 0. Let me double check if there's something wrong. It's 1 bit, and it's going to be 0. Yeah, I don't think we're missing anything. So in step 2, while select signal is still 1, we change B to 1, from 0 to 1. This won't do anything, because if you check the sensitivity list of this always block, it's only cell. So this block will be executed only when the cell signal changes value. So when B changes, it's like when the value of B changes, nothing will change. The block won't execute, basically. And then because the block doesn't execute, none of the values here change. And that's the solution, basically, in step 2. The always block is not executed, so temp is still 1, and out is still 0. Do you have any questions about this one? Okay, then it's the final question for this problem. There's another code, and it's asking if the code is syntactically correct and will result in deterministic values for all signals. And if not, please explain. So this module has 2-bit inputs in 1. Okay, in 1 is 2 bits, but in 2 is also 2-bit. Yeah, I guess. anyways, it's not going to be important in the end for this question. And there's an input called op and an output, 2-bit output register Z and S. It's a 1-bit output register. And there's a wire declaration here named temp, TMP. And then we have an always statement that makes an assignment to this TMP as in10 and in20. So this is the first mistake. The problem here is because this TMP is declared as a wire, and we're making an assignment to it in an always block. So that's not correct. Basically, this should either, so this is incorrect as problem 1. And to solve this, we can either make, well, TMP definition or declaration should be register. Right? Or we somehow remove this assignment from the always block and make it a assignment outside the always block by using assign statement, for example. In the next line, we have an assignment to Z, and then it's TMP and OP. This looks fine. There's nothing wrong with this line. And then the second always block, we have another assignment to temp. So this is another problem. Because we already have an assignment to TMP in the first always block, the second always block has the same sensitivity list, and it's making an assignment to the same value. Well, because TMP is wire, this is wrong to begin with, but even if TMP was a register, this would be wrong. And I think the easy way to think about it is when you have two always blocks, you don't know when they will execute in the real sense. So you have two combinational circuits driving the same signal. But those circuits can be different. And how do you connect two output wires of two circuits to a single wire without using any gates and stuff? And this is the problem here, basically. So I think this is called multiple drivers issue. So I will just write it that way. So there are multiple drivers of TMP. So this should not happen. And this is the second problem. The final in this line, we don't have a problem here because Z is a register here, defined as a register, and we're making an assignment to it in an always block. Yes. I think so. I think this is this should be OP. Yeah. Yeah, but I mean, if you notice this and like in the exam said that P doesn't exist, probably it's yeah. In the solution we don't have that, so I'm assuming this is a mistake. But you're right, P is not declared. Well, for at least in Verilog, well, in Vivado, what happens is I think it will, if the compiler cannot find the definition of a variable, it will just put a 0 over there. But either way, it's fine, I think. Yeah, and finally, we have this assign statement here. We're making an assignment to S, but S is defined as a register, and this is the third problem. So we cannot use assign statements outside the always blocks to make assignments to registers. So this should have been defined as a wire. And to fix this, we can change the definition of S. Should be wire. Or we move this inside an always block if you want to have the same behavior. Any questions here? Okay, if not, we're done with this problem. And we can move on to the next one. Yeah, for that, I'll be going and giving the stage to Mohammed.
Okay. The next question is about Boolean circuit minimization, which actually usually they are the simple exam questions. So the first one is so we need to rewrite this equation to make it only using NAND operations. So to solve such question, usually a good strategy is to use not. So we do not plus C bar A bar C bar. Yeah. Thank you. Then, so A bar not is A bar. So it is AB dot C bar dot A bar C bar and bar. So we can actually rewrite this question and this part, which is C bar, A bar, C bar, and then we don't need to write C bar. So we reach to AB dot AC bar bar. And now we can see that here we have a NAND operation. The overall is a NAND operation, but this one needs to be a NAND operation. And for that, the only thing we need to do is and that's all. Any question? It's kind of easy. So part B. So we need to write the function formula and then try to simplify it with Boolean equations. So the function is based on the mean terms that we have here is A bar, B bar, C bar, D bar plus A bar, B, C bar, D bar plus A bar, B, C bar, D. Okay. A, B bar, C bar, D plus A, B, C bar, D. So you need to find common terms and try to factor them out. So we have A bar, C bar, D bar in both first two terms. So we factor A bar, B bar, D bar. And then we have C bar plus C. A bar, B, C bar, D bar. A bar, B, C bar, D. Yeah, you are right. This is A, B bar, C bar, D bar. A, B, A, B, C bar, D bar. Yeah, thank you. So here if we factor A bar, B bar, D bar, no, A bar, D bar, C bar. Then we have B bar plus B So we cancel down these two terms. Here we have A bar, B, C bar, D, and we can find similar one. Yeah, these two. So B, C bar, D, we reach to this one. And also we have these two terms, A, C bar, D bar, B bar plus B. So these items are, these are one. So we reach to A bar, C bar, D bar, plus or B, C bar, D, or A, C bar, D bar. Okay, then we can also cancel these two terms and we reach to C bar, D bar, plus or B, C bar, D. And we can factor out C bar. This is D bar or B and D, which then we can also simplify this to D bar or B. Yeah. Any question? Okay. Banu?
So the next question is about finite state machines. Okay. So first, it says that you're going to need a Moore finite state machine. So you have to draw the circuit not the circuit, but the machine accordingly. And it's going to detect a bit pattern, which is 0, 1, 1, on like streaming input from X. And when it detects a 0, 1, 1 pattern, the 1-bit output Y is going to be 1. So this is like you have some patterns, and then you're going to have 1, 0, then 1, 1, then 1, 1, and then the remaining doesn't matter. But at this time, the output Y should be 1. And how you start is the initial bit value of X is 0. So in your first reset state, which is S0, you assume that you have X equals to 0. So you have a pattern that is like some pattern and ends with 0. And since you did not observe 1, 1, the last bit is 0, your Y should be equal to 0. And since this is a Moore finite state machine, your output only depends on the state you are in. Then if you have, for example, another 0, then still your last bit is 0. So if X is equal to 0, you stay in the same state. But if your X equals to 1, then you go to another state, which is a pattern, which is I mean, just describes a pattern that like the initials are not important, but it ends with 0, 1. So in this one, if you got any 0, then your pattern becomes something 0. So you have to go to this initial state where the last bit is 0, where the last bit you observed is 0. And in this one, the output is also 0 again, because you didn't observe 0, 1, 1 yet. And if you observe 1 in this state, then you will see the pattern, and then you need to go to another state which says, okay, this is X equals to 1. And in this state, you observed a pattern, but this pattern ended with 0, 1, 1. So this pattern, the output should be 1 because you observed your pattern. And if you observe a 0 in this state, you have to go to this S0 again, because this is a state where you have a pattern that ends with 0 only. But if you observe a 1, you have to go to another state, which is a state where you observed a pattern that ends with 0 directly. So it's not like you did not observe your target pattern, any bit of your target pattern yet. And if you observe 1 in this state, you have nothing new in your pattern, so you stay in your pattern, so you stay in your state. But if you observe a 0 in this state, you actually go to the initial state, which is x equals to 0, because you observed a bit pattern that ends with 0, and this state encloses this one. The last thing remaining is what is going to be the output in this state, and this should be 0 because you did not observe the bit pattern you target yet in this state. So do you have any questions about this state machine diagram? Yep. Yeah, but in this one, it says just assume that you have a 0 initially. So you don't like search for the first 0 because it's already given when you start your finite state machine. That's why we start in S0 and then we search for 1 directly instead of searching for 0. Otherwise, we would start in this S3 state and we would search for 0 first. But this in reset. Mm-hmm. Yeah, 1. That's why we start here with reset and then we search for 1. But in this one, when we reach the pattern first, we go to this one again if there is 0. But let's say we start with 1. From here, we search for 0 and then go to this one yet. But like this question just says initial bit value of x is 0. It could be 1 as well. There's no specific reason why it's 0. But if it's 0, what? Yeah, it could be nothing, yes. And yeah, and like what I would do if I were you, if nothing is specified, you can just say, I assume this. If it's not clearly stated in the question, you can just say, I assume this, and I draw the state machine according to that, if nothing is specified already. Any other question? Okay. So the next part of the question is about simplifying a finite state machine that is given to you. But the first small question is the type of the finite state machine. Is this a Mealy or Moore machine? So the difference between these two finite state machines is that if the output depends on the state you are in, or the output depends on the state you are in and the input that you have. And in this state machine diagram, if you can see, the outputs are here and the inputs are here. So the output depends both on from which state you are traveling to which state and then the input. So for example, if you're in this state, the input is 1, you get 0. This is not a good example. If you are in this state, for example, if your input is 0, your output is 0 as well. But if your input is 1, your output is 1. So it depends on the input as well. Then this is why this is a Mealy machine. And the next question is about whether you can simplify the state diagram such that you reduce the number of states. And if you can do that, the question asks you to draw a new finite state machine with the minimum number of states. So what you can do is to first maybe try to understand what this finite state machine is doing. But even before that, you can see that this state is never reached because you stay in this S2. You start with this S2 and then there's no edge that's going to S0. So you can just maybe even delete this part of the FSM. And for the remaining 3 states, we know that S2 should be here for sure because this is a reset state. And then you start with S2 with reset. And if it's 0, you stay here as 0, 0. Okay. Well, what about S1 and S3? Are there any redundancies here? Maybe we can check. So if it's 0, we stay here. But if it's 1, we go to 1 with the output 1. But if we get another 1, we go to this state, which is 0. And it's like S1 and S3 behave similarly when they receive 0. Both go to S2 state with output 1. So we can maybe just think that they behave similarly, because if they receive a 1, for the first time they output 1, but the other ones they just stay, for example, S3 stays here and then output 0. So and then this one goes to here, and then S3 stays like in the remaining ones you stay here. So maybe we can just remove the redundancy in S1 by removing this and then converting this arrow from here to here, and then we do 1 1 here, because for the next ones and then the zeros, S1 and S3 behave identically. So we can have it as 1 1 to S3, and then we stay here if it's 1, and then we go to the initial state if the input is 0. And then this is going to be the the simplified state diagram for the circuit the machine given above. Do you have any questions about how I simplified it? And okay, so there's this one last question, which is like the purpose of this machine and for what purpose can it be useful. So we can first check maybe what it's doing, what kind of input it's capturing. We see that we start with as a diagram, and if it's 0, we just stay there. But if we have a pattern that's 0 0 0, and then we have 1, we have an output here. And then if we have remaining ones, we don't have any output. Like we have output 0, I mean. And then if we have any zeros, then you again have an output 1. And this pattern goes like this. So you have outputs when your input transitions from 0 to 1 or 1 to 0. So it's kind of like detects the edges from 0 1 to 1 0. Yep, that's kind of all. Do you have any questions? This part? No, I guess. Okay.
Can you hear me? Yeah. So let's look at fourth question. It's a relatively simpler question to answer with two options for every question. So the question goes like this. So it tests the understanding of ISA instruction set architecture and microarchitecture. So a new CPU has two comprehensive user manuals available for purchase as shown in table 1. So you have the isa.pdf and the microarchitecture.pdf. ISA, the manual costs 1 million francs, and it gives the ISA in detail. And the microarchitecture manual gives details on the microarchitecture, and it costs 10 million francs. So unfortunately, the manuals are extremely expensive, and you can only afford one of the two. If both manuals might be useful, you would prefer the cheaper one. So for each of the following questions you would like to answer, decide which manual is more likely to help. So for this question, if there is an incorrect answer, we'll subtract 1 point, and if there is no answer for some of the questions, we'll award 0 points. So let's look at a very simple diagram of where ISA sits. ISA is like an interface between the programmer and the hardware or the microarchitecture. So here you have, and it gives a kind of a model for the programmer to understand the processor and its workings. So languages
like assembly or higher level languages will use the instruction set architecture to basically do the program. And so you have C++ and so on. So let's look at each of these questions. So the integer multiplication algorithm used by the ALU. So this is something which is very, very specific to the ALU or the microarchitecture, and this is not exposed to the programmer. So the answer for this is microarchitecture. And the second question is the program counter width. So here, this is something which will be specified in both the ISA and the microarchitecture. So basically, the program counter will tell us what is the next instruction that gets executed or the address of the next instruction. So the width is also specified in the ISA, and that typically tells us the width of the address bus. And that is required by the programmer to basically understand uh, um, the current instruction that is being executed and things like that. So the answer for this is the ISA. Next question is branch misprediction penalty. So branch prediction is typically transparent to the programmer. But I mean, sometimes the compiler can give hints to the for successful branch prediction. But the penalty is something which the programmer will not know, and the penalty is usually calculated by the number of cycles which were wasted by the misprediction. So this again is the micro specified in the microarchitecture. Again, in the second question, since it could be specified in both the manuals, we still go with the ISA because it's the cheaper one. And the ability to flush the TLB from the OS. So TLB flush is something that is triggered by the kernel or the operating system. So when the software page tables are updated and the TLB has to be flushed because it has stale information. So the OS will use some registers provided by the which are mentioned in the ISA to trigger the TLB flush. So this would be this can be found in the ISA, and the size of the reorder buffer in an out of order CPU. So again, the reorder buffer is something which is still which is again transparent to the programmer, and it is specific to the microarchitecture. So the size of the reorder buffer is something which the programmer wouldn't know. So the ISA does not mention that anywhere. So it's in the microarchitecture.pdf. Any questions so far? So the fetch width of a superscalar CPU. So in a superscalar CPU, you can handle multiple instructions in a single cycle in the pipeline. So the fetch width is again something which the ISA does not provide because it's not something that the programmer can have any control on. So so this is specific to the microarchitecture and it's in that manual. And SIMD instruction support. So SIMD is basically a single instruction which operates on multiple data elements. So this is the basis for vector processing, and SIMD needs support in both hardware and software. So if you would find mention of SIMD in both ISA and the microarchitecture PDF. If you want to look at whether the SIMD is supported, it would be available in isa.pdf if there is support. And the memory address, the next question is the memory addresses of the memory map devices of the CPU, example keyboard. So if a programmer has to write drivers for the keyboard or mouse, which is basically memory map devices, uh, the programmer has to know the memory address of these devices. So that would be something which would be available in the isa.pdf. And the number of non-programmable registers in the CPU. So you have both programmable registers and non-programmable registers. So programmable registers are typically mentioned in the ISA, but then non-programmable registers are something which the microarchitecture or the CPU uses for its internal purposes. So that would not find mention. That is not mentioned in the ISA, and it would be available only in the microarchitecture. Any questions so far? So the next question is the replacement policy of the L1 data cache. The multi-level caches are transparent to the programmer or to the higher level abstraction. So it's not it, so the ISA wouldn't actually provide any information on the L1 data cache or the replacement policy of that. Uh, you would typically find mention of the cache sizes, but the replacement policy is something which would not be available in the ISA, and that would be there in the microarchitecture. You can only find it in the microarchitecture manual. Yeah. Sure. Thanks. Okay. The next question is the memory controller's scheduling algorithm. Again, this is something internal to the microarchitecture and would not be exposed to the ISA or the programmer. So this is available in the microarchitecture PDF. The next question is the number of bits required for the destination register of a load instruction. So typically in the instruction set, you would find the width of the source and the destination registers for all the instructions. So that should be available in the isa.pdf. And the next one is pretty easy. So description of support for division and multiplication between registers. So if there is support for these two operations, it would be available in the ISA. And yeah, then 14th question is the mechanism to enter in a system call in the OS. So when an application wants to enter a system call, it has to typically execute a software interrupt or something called the trap instruction, which should be mentioned in the ISA manual. So that's again the ISA.pdf. So any thumb rule is anything which is performed by the OS or the application is something that needs to be mentioned in the ISA. And the last question is the size of addressable memory. So so this is something which the programmer should know when allocating memory for the applications, or when basically to know the virtual memory and the physical memory sizes. So that should also be available in the isa.pdf. Yeah. So yeah. Any questions? Okay. Thank you.
goes wrong. Is this like this? The other way around? Like this? It's wrong. Okay. 4 years seeing and didn't learn yet. But anyway. Hello everyone. So hopefully you can hear me. Does it look good? Yes. So I'm going to solve the performance evaluation question once again. And I guess the best tip that I can give you to a performance evaluation question is read the question really carefully, because often the answer is quite simple. So let's just read it. So cycle processor P1 execute load instructions in 10 cycles, store instructions in 8 cycles, arithmetic instructions in 4 cycles, and branch instructions in 4 cycles. Consider application A, where 20% of all instructions are load instructions, 20% of all instructions are store instructions, 50% of all instructions are arithmetic instructions, and 10% of all instructions are branch instructions. And so the question starts, what is the CPI of application A when executing on processor P1? Show your work. So basically, to calculate the average CPI, you basically multiply the number of cycles that it's going to take for a type of operation to the amount of instructions that the application is going to execute. So because this is cycle per instructions, right? So the CPI here is going to be load instructions takes 10 cycles times the number of load instructions that you have, or the breakdown, which is 20%. So times 0.2 plus store instructions takes 8 cycles times how much store instructions you have, 20%, 2.2. Arithmetic instructions takes 4 cycles times the amount of arithmetic instructions that you have, 50%, plus you have 4 cycles for branch instructions, and the latency of the amount of branches that you have, 10%. And I'm not going to make the math, I'm going to look at here. So it's going to give 6. Really important, I think I said this last time, in the exam, more important that get this 6 correct, like the number 6. More important than this is to have the equation correct. So even though if you make some mistake when you're doing the math, if you leave the equation clear enough so the TA can understand what you were thinking when you are creating the solution, you're not going to be deducted so many points at all for math mistakes. So any question related to this? Okay, good. So part B now. A new design of the processor doubles the clock frequency of P1. However, the latency of the load, store, arithmetic, and branch instructions increases by 2, 2, 2, and 1 cycles respectively. So we call this new processor P2. The compiler used to generate instructions for P2 is the same as P1. All of this is going to be relevant in the next question. Thus, it produces the same number of instructions for program A. What is the CPI of application A when executing processor C2? Show your work. So it's pretty much CPI P2. Let me put here P1. Pretty much the same that we did, but you are going to include those latencies here on the CPI calculation. So since we say in the question that the compiler is the same, the breakdown of instructions is going to be exactly the same, so you can keep this. The only thing that you need to do is add the number of latencies, the added latencies. So we have the original 10 cycles for load instructions, plus you're adding 2 cycles for load instructions. So plus 2 times the amount of load instructions that is executed, 0.2, plus original latency for store instructions is 8, plus you also add 2 to store instructions times the 20% of load instructions that are executed, plus original latency of arithmetic instructions, plus how many cycles was added, 2 times the 0.5, plus original latency of branch instructions, 4, plus
one cycle that was added to branches and the amount of branches that are executed. And this is equals to 7.9. Okay, any question? Okay, maybe not. So then it asks which processor is faster, P1 or P2, and by how much, and show your work. Again, the most important, I said this last time also, really important equation to remember is the execution time equation. So execution time is equals to the number of instructions times the CPI times 1 over the clock frequency. So we are going to assemble both instructions for both processors. So execution time of processor 1 is going to be the number of instructions that is execute times the CPI that we calculate in the previous question. So 6 times 1 over its frequency. And the execution time or P2 is going to be the number of instructions times the CPI that I calculated in the previous question, 7.9, times, from the other question, we saw that the new design doubles the clock frequency, right? So if the frequency was 1 over F, this is going to be 1 over 2F, right? So now you basically need to calculate to inequality to see which processor is faster. So for example, we can assume that P2 is faster than P1. So if you assume the execution time or P2 is smaller the execution time of P1, this means that the execution time of P2 divided by the execution time of P1 smaller than 1, then you just verify if the inequality is true or not. So you can put the values here. Is going to be number of instructions times 6 times 1 over F divided by number of instructions times 7.9 times 1 over 2F. And you can simplify the equation. And then I'm going to, again, check the solution because I don't want to do the math. And this is going to give 1.52. So this means that P2 is faster than P1 by 1.52 times. Okay, is there any question here? Okay, good. So the last part of the question, this one. Okay. Hopefully you can see it. So there is some extra area in the chip of processor P1 where extra hardware can fit. You can decide to include in your processor a faster branch execution unit or a faster memory device. The faster branch execution unit reduces the latency of branch instructions by a factor of 4, and the memory device reduces the latency of memory operation by a factor of 2. Which design do you choose? You can use the same equation here again of the execution time and calculate for the branch and for the memory device again, but it's more cumbersome. There is the Abdom's law that we learned in, I think it was lecture 20. So we have this formula here, 1 over 1 minus the portion that you optimize plus the portion that you optimize divided by the speed up of the speed up for the optimization that you provide. So let's apply this equation for both branches and memory units. So let's see the speed up of having a faster branch unit. This is going to be 1 over 1 minus the portion that you're optimizing, right? If you look back at the equation of the question, 10% of all of the operations are branch instructions. So you're going to be optimizing, if you choose the branch, only 10% of the total execution. So it's going to be 0.1, because this is normalized, plus the portion that you optimize, 0.1, divided by how much you're optimizing that portion. So you're optimizing branch units or branch instructions by 4 times. So this is divided by 4. If you do the math, I'm going to check here. This is 1.08. Then you do the same for the memory. 1 over 1 minus the portion that you're optimizing, right? This is a memory unit, right? So this memory unit support both load and store operations. So you have 20% of all of the instructions are loads and 20% of all of the instructions are stores, right? So this is 0.2 plus 0.2. This is for the loads. This is for the stores. Plus portion that you are optimizing, 0.2 plus 0.2, divided by how much you're optimizing that portion, factor of 2. And this is equals to, sorry, let me see here, 1.25. So you pick the one that gives you the highest speed up, right? So you pick choose the memory unit optimization. So it's basically this. Is there any question? Yes, I was just want to show something different how to do. So if you look at the equation, the solution here, I give the solution for using Abram's law, as I just did. And there is the alternative solution here, which basically recalculates CPI as we did in portion A and B in the question. That might be more straightforward, but requires more math, I guess. So if you remember Abram's law from the top of your mind, which is extremely important, it's going to be much faster. Any other question? Okay, thank you so much.
Okay, does this work? Yeah. So we're doing the pipeline reverse engineering question. So we get a pseudocode, well, not a pseudocode, assembly code. And we should answer various questions about how this processor probably looks based on the cycle numbers we get. And then afterwards we should also count how many cycles the program executes, this kind of thing. So let's see. Let's look at the code first. So we first load two registers, R1 and R2 with immediates. And then we know that, okay, these get used in to increment the counter. There's some kind of multiplication going on, some kind of loop bounce check. And if the loop is taken, it jumps back to L1. So first question we should answer is list the necessary data forwardings between pipelining stages to exhibit this behavior. So this behavior here means the behavior we see in the execution timeline, specifically the stalls we are seeing. So we need some specific data forwarding paths to cause exactly these cycles of stalls. So let's see where the data goes. So we have a stall for dynamic instruction number 3, where cycles 5 and 6 stall. That is the execute stage. Somehow is awaiting the input values R1 and R2. So specifically the R2 value from the second dynamic instruction. So from the execute stage 3 to here, we are awaiting this value. So that's one path we're getting, and we're getting at least also the R1 from here to here. And we notice that at least at this point, the value must have been ready because execute of add starts here already. If we didn't have the value, the execute stage of the addition couldn't start. Okay, so we know that. And then we have some more stalls to look at. We have also a stall in cycle 9. As you can see in cycle 9 is we are awaiting the R1 value from the addition up here. So let's see, this is the result from this execution is available to start execution 1 here. So what we see both times is that at least there must be forwarding from E3 to E1. That's as if, yeah, that has to be at least there, so we are not stalling longer here. And the second thing we're seeing in the remaining stall is that the jump condition, so jump 0, should be actually jump not 0. Yeah, I guess there's still an issue in the question here. This should be jump not 0. So this this jump condition is checked here in E1, and it awaits the value from this subtraction. So it jumps if this subtraction is not 0. So we also have some kind of forwarding path there from E3 to E1. So we're also forwarding oh, thank you. So we're also, let me check. Yeah, we're also forwarding the condition registers. Okay, so yeah, the reason we see this is that the execute stage 1 of jump not 0 starts the next cycle after we got the subtraction result. Okay, so that's question A. Is there a question to here? Great. All right. So does this machine use hardware interlocking or software interlocking? Well, so software interlocking would be that there will be some kind of no ops in the assembly code. Hardware interlocking here means that the machine automatically detects that there are data dependencies and it automatically stalls until it can resolve these data dependencies. So there is hardware interlocking because of two reasons. There are no knobs in the assembly code. And machine stalls by itself when necessary. Okay. On to question C. So we should we're asked to rewrite these the execution timeline basically. So before we answered in B that we had hardware interlocking, and now we should do the opposite. So we should do software interlocking, and we basically should rewrite this execution timeline accordingly. So what we need to do is we take the instructions we had before, we insert knobs in between as needed to account for these stalls that would happen with hardware interlocking, and write down the cycle timeline. So let's see. I'll number my dynamic instructions 0 based, so it makes a bit more sense in the next sub question, but you could also start with 1 here. Okay, so the first instruction is this move immediate. So this is fetch, decode, execute 1, execute 2, 3, memory, and write back. Second instruction is move E, R1, Y, fetch, decode, 1, 2, 3, memory, and we should continue the table down here. Sorry, this should be R2. Okay. So third instruction is this addition, but there's a stall first. So as you can see over here, the addition, if you had hardware interlocking, the addition would later stall to await the value from the move instruction. And in software interlocking, we cannot make the machine stall automatically because it doesn't have the data already, right? So we need to insert knobs so that there are no stalls happening later. So we need, to account for this 2-cycle stall here, basically we need to insert 2 cycle verbs of knobs. So let's write also the timeline here, fetch, decode, E1, 2, E3. Okay, so these are knob, knob. No idea why I started here with 1. This should be, oh, this 1, 2, 3. Okay. Let's see. So we got our stall accounted for. We can continue with the add instruction. We add R1, 1, 2. Okay. Let's see. So after the add, the multiplication executes immediately. So the multiplication also stalls, but only because the addition was stalled first. We've already accounted for this with no ops. There's no additional stalls in the multiplication, so there are no ops needed here. Okay. And now we have a sub instruction. Let's see, in the hard interlocking case, there was a stall here because we were waiting for the result from the addition. So we cannot start with the sub directly here. We should have a NOP again, and then we can have sub. All right. And finally, we have this jump instruction. So this has 2 additional stalls on top of what sub I already stalled, because it's waiting for the result from the subtraction. So there's 2 more knobs needed here. Let's only write them down here, maybe. And finally, we have now the jump. Well, it should be a jump, not 0. Yeah. Okay. So that's this exercise. Are there any questions here? No? Good. Yeah, as you can see, this table is a bit boring, and the interesting part is probably where to insert the knobs exactly. All right, so we need this result for the next sub-exercise. So we get some additional information. We know now that they're both 1. And then I have some information about what the branch behavior looks like. We are asked to calculate t, so what the current clock cycle is, if currently the value of R1 is 98, and we are currently fetching the addition. So let me show you the code again. So we know that these 2 both get initialized to 1. We know that the value that's currently stored in R1 after some execution is 98. And we know that we are currently fetching this instruction here. So this is really an increment. If you initialize both of these to 1, then this addition is really R1 plus equals 1. Okay, so what this means is Let me see. I wrote this down very nicely. Somewhere. Okay, so we know the loop counter here. So really the code, what the code ends up being is you have some kind of loop and you initialize some kind of loop counter R1 to 1. It's given up here. And you have some kind of increment that you initialize to 1 also. And then at the start of every iteration, you increment your loop counter. You do some kind of calculation. Here you check if your loop counter is exactly 100. And if it is exactly 100, you stop the loop. So you should write some kind of explanation here like this. And what this should result at is that if currently R1 is 98, then we have already executed, or well, then R1 has already been incremented. And 97 times, right? It started out at 1 and it incremented 97 times. Now it's at 98. And of the current iteration, because we're currently, according to the exercise, we're currently fetching this increment. Of the current iteration, the increment hasn't happened yet. And so there have been 97 past iterations, and we are currently at the start of the 98th iteration. Okay, so far so good. Now we take this information and we have to calculate cycles. Fortunately, we already have this table over here, which makes the cycle count much easier. Although this machine uses hardware interlocking, we get the equivalent cycle counts with software interlocking. So we can really easily check how many cycles a certain range of code takes. So let's see, so the first iteration goes from dynamic instruction number 0 to dynamic instruction number 10, because you have these two additional initialization operations and knobs. So this is 11 cycles. So first iteration, 11 cycles. And then any further iterations, the jump would go right up here, right? So we go from here to right here. And you don't need to redo the knobs. There's no benefit to that. You start with the addition immediately. And this is what 1, 2, 3, 4, 5, 6, 7 instructions. So 7 cycles. So the next 96 iterations take 7 cycles each. And then of the last iteration, since we're currently only fetching the first instruction of the last iteration, there have no cycles been spent in that iteration. So we just have to calculate the 11 plus 96 times 7. And there's some math for you to do. And I calculated that's 682. Okay. It could be, depending on how you number instructions here. So I started with 0. If you number instructions here from 1, like it's done over here, then you might end up at 683 here. It doesn't really matter. It's good that you just write down whatever you assumed here, if you count it 0 based or 1 based. Yeah? Yeah, it's a great question. So I'll repeat it for the recording quickly. So the question was if you have this jump here, this solution here assumes that there's no kind of delay, or well, stall wouldn't be accurate, but there's no delay between here and starting the addition instruction here, even though we need some time to probably even realize that this is a branch. And that's, yeah, a good point. The master solution that we have for this question kind of assumes that there is no such delay. This is possible if you have, for example, a processor where in the fetch stage, you can immediately check that it's a jump instruction, and you can immediately get the jump target. Then this could kind of work, and then your branch predictor predicts always taken, and you wouldn't get a stall. So it's probably good, and unfortunately the master solution doesn't do this, but it's probably good to write here. By the way, this is assuming the branch target is available after fetch stage. Right? Then you don't get the stall, and it all works out. But you're entirely correct if you assume something else, for example, that the branch target is available after decode, maybe, which is maybe a bit more standard. Then you would have at least one cycle additional delay there. Yeah, it wouldn't be really a stall. It would probably be the pipeline being flushed. But anyway, yes, that would change the calculation a little bit. If you write this assumption in your solution, then that's entirely correct. Is that good? Maybe another question. Does it matter? I mean, you could get it completely wrong. You could say like 2,000, or you could say like 1 by 4 by 1 or 2 errors. Like you certain differently than the rest. I mean, if you get 600, I mean, we don't just look at your number and see is that the number on the master solution. What's more important than the final number is like how it derived this. Hopefully, if you're off by 1, then 90% of your derivation is correct. So there should be some points. Yeah. Sure. All right. So finally, a bit of an easy question. We should calculate n. So this is the dynamic instruction number. So what we really asked is, given that we are in the 98th iteration, how many instructions have executed so far? We are fetching this one. What's the index of this? What's the dynamic instruction number of this instruction when you're fetching it in the 98th iteration? That should be a super simple question, because you simply have these 2 instructions there before the loop, plus, let's see, 97 iterations that you already completed of 4 instructions each. And then, well, the current one, depending if you're 0-based or 1-based, if we're 0-based, it's exactly this number. Otherwise, it would be +1. And we also already calculated this. It's 390. Yeah. And well, you should write a little bit of text there, right? How you arrived at these numbers, why you got to this multiplication. Questions? Okay, great. Thanks, then I'm done. Is the mic off? Can you tell me quickly how to like I place the sheet here and then I solve it, right? So you're going like this. Interesting. So, but how do you do? How do you do? How did you do it? Right. So, yeah, exactly right. You can move it up and down. Okay. Zoom in and down. Perfect. Yeah. Great. Right. So, do we start? Like, is it on? Can you hear me? Is the mic is on, right? Perfect. Okay. All right. So today I will discuss the Tomasulo's algorithm question. Now, this is an important question. So before we discuss this question, I would like to give you some exam tips. If 6 months ago I wrote the same exam and I got a good score, so I would really like you to do well. So the first tip that I would like to give you is like, take a deep breath, just relax, try to understand the question, okay? Read the question first. You would be surprised how many people make mistakes simply because they don't read the question. Form a mental diagram of what you're going to do, form an image of the question in your head, and then try to solve it. All right, so I'll illustrate this process so you can get an idea of what I'm trying to say. Now, this question says that we want to deal with Tomasulo's algorithm. We want to reverse engineer a processor's implementation for this Tomasulo algorithm. Let's start reading the question. Okay, so as I just said, read the question carefully. We consider a scalar processor with in-order fetch, out-of-order dispatch, and in-order retirement execution engine. All right, so you have, I can write on this? Not on this, right? All right, so yeah. You can see clearly that we have a scalar processor. I hope you know the word scalar. It means simple, not vector. Draw the processor, draw the box, okay? You have in order fetch, you have out of order dispatch, and you have in order retirement, okay? Good, we got that down. Now, this processor has 4 main pipeline stages. You have fetch, decode, execute, and you have write back, okay? Right, just see that I'm just trying to understand the question. I'm not trying to solve it right now. The processor implements a single level data cache. All right, this is our cache. Up next, the processor has following 2 types of execution units. It has an ALU and it has a memory unit, but we do not know how many of these units the processor has. All right, now let's draw these on our diagram. You have the ALU right here, and you have the memory unit right here. Now, notice that I gave some space. I left this space because the question explicitly mentions we do not know how many of these units are there, right? So there is still scope to expand it in our mental image. Perfect. So the ALU executes integer instructions. It clearly specifies which instructions. Those would be addition, multiplication, move, and branch. And the memory unit executes load and store instructions. Okay, this is known stuff. This is nothing new. We know this already. So ALU would be all add, multiply, right? And the memory unit would be, this is the most important part,
load store instruction. So always remember, when you see Tomasulo, load stores are going to be your problem. Be careful with the load stores and everything else will be okay. Okay. Right. Up next, we see the question says, the processor is connected to a main memory that has a fixed access. All right. So let's say that this is the main memory. And all right, we got the main memory down here. Next, the question says, load store instructions spend cycles in the E stage exclusively for accessing the data cache and the main memory. Right, so what does this statement mean? We saw that we have these pipeline execution stages. This question is saying that if I do a load store, I will do a fetch, then I'll do a decode, then I'll do a execute, and then I'll do a write back. But if this data is not in the cache, then I will have to wait in the execute stage. And this is your key, right? So I told you, the question is very simple. You just need to read it carefully. This point clearly tells you that if there's going to be a load store that is going to miss in the cache, then this execute stage will be the one that is stuck, okay? So we will see up next why this is a very important point. Okay. And finally, the question tells us there are 2 reservation stations, one for each execution unit type. Let's draw the reservation stations. This is the execution unit, ALU and memory, and this is the reservation station. The reservation station reserves the instructions before they're scheduled for execution, okay? The reservation stations are all initially empty. The processor executes an arbitrary program. All right, so arbitrary might sound confusing or difficult, but always remember, the question is meant to be solved, okay? This question does not have anything that is not known to you. It is designed to be solved. So if you just read it carefully and do not get thrown back by these kind of words, you will do it. So from the beginning of the program until the program execution finishes, 7 dynamic instructions enter the processor pipeline. Notice the word dynamic. That is your hint that these instructions might be scheduled differently. You know, dynamic could be anything. It could be waiting because of loads. It could be branch prediction. It could be Tomasulo. So yeah, I'm just trying to build up the environment of how you should think in order to get this right. Now, table 3 shows the 7 instructions and their execution diagram. All right, this is perfect. So the question has given us the exact execution diagram for how these instructions will be scheduled. Up next, we see the instruction semantics, which tells us, okay, what the instruction means and what it does. Let's keep this at the back of our head and right now focus on this very interesting new data point that we've got. That would be the table 3. As we look into the table 3, we will come back to the instruction semantics to understand what each instruction does. Now, in table 3, I start reading table 3 and I see that the first instruction is a move instruction. Remember our diagram? I told you to be careful about load stores. So whenever you see a load and store instruction, be careful about that. Right now, I see a move instruction, which I know is not a load store. So, okay, this should be easy. All right, so I see it does a fetch, it does a decode, then it does a execute with 4 stages, and then it does a write back. Okay, sounds good. I know this. Up next, I see a load. All right, now your buzzers should be ringing or something. It says load R1, R0. So it loads a value at address R0 into R1. And now I see it does a fetch, it does a decode, and then it stalls, okay? Why does it stall? It stalls because I see E1, E2, E3, E4 are going, it's used in the just previous, in the previous instruction, all right? Up next, I see that it executes 8 cycles in the E stage. This question gave us a very important data point. If you remember, it said clearly that the, yes, load store instructions, I hope you can see this. Load store instructions spend cycles in the E stage exclusively for accessing the data cache, okay? We should connect this point at this stage to this instruction and see that, okay, this is 8 instructions, there are 8 cycles, not instructions, that are being spent in this stage waiting for the cache. That means this is the memory access, and we don't know if it was a hit or a miss. But yeah, I'm trying to get you to flow with the question, see what the data is given to you, because at the end of the day, remember that it is meant to be solved. Do not be thrown off by it. All right, up next we have branch if less than R1. All right, and I see that it does fetch, decode. It is waiting until this execution stage gets freed, and then it does E1, E2, E3, E4. That sounds good. I mean, that means that I could not schedule it immediately, but yeah, there was no waiting or there was no load stores in this. Perfect. Up next, I see this very interesting data point called squashed. Okay. Bringing you back to the instructions that were given in the question. Remember this word dynamic? Whenever you see dynamic, think of memory or think of branch predictors. Okay? Like it usually almost always means memory or branch predictors. Now, we see that this was squashed. Squashed means this instruction was getting executed, but in the middle, the processor said, no, this result does not matter. I'm not going to care about it. I will kill this right away. So it's called in-flight termination of the instruction. You see that both of these instructions were squashed. That means there was most likely a branch predictor or a cache access at this point. Now, do we see a load instruction before this? No. We see a branch instruction before this, right? That means most likely this was a branch miss. And these instructions were squashed because we took the wrong branch that we were not supposed to take, and now we should correct our path. And that means we take the next instruction that was executed correctly after these. Now, what does correct execution mean? Correct execution means this instruction was executed to completion. Completion is very important. This W, you see, this W means write back. It means the instruction was completed. It was not killed in between. I hope that's very clear. So putting it all together, what we see has happened here is that this branch lesson instruction has now jumped to this one, okay? And these two, they got killed, okay? Now, I can understand that at the first look, it might seem complex, but yeah, just hold on and we'll come back and you'll see how it all makes sense. Finally, we have another store instruction. Coming back to the very important point that we saw, load store instructions spend cycles in the E stage exclusively for accessing the data cache or the main memory. So now we see that this store instruction is accessing a memory value. It's accessing R0. And if you remember in the first instruction, this was also accessing R0, and we did not update R0 at any point. So this means that this is also accessing the same memory location. And another very beautiful point here that you can see this E1 is, it takes just a single cycle. So this instruction spends a single cycle in the execute stage compared to this one, this load instruction, which spent 8 cycles in the execute stage. Do you notice the difference? Can you guess where would this difference come from? Most likely a cache miss. Yeah, you're absolutely right. All right, so yeah, we have set up the premise of the question. I can take questions afterwards. I would like to complete this on time. Okay, good. So yeah, we've just read the question. I've not solved anything so far. You have to read the question first carefully. Right now, all I have done is created a mental image for this question, right? You have unlimited supply of paper in the exam. Use that paper to create this mental image. Do not try to solve it like haphazardly. Okay, now let's take a look at the questions, and then we'll try to fill in the gaps in this mental image that we have. So the first question that we have is, what is the cache hit latency? If I say cache hit latency, immediately your mind should come to, oh, cache would be somewhere on the load store path, right? And we saw that we have load store instructions for the same address, which had different access latencies, right? You remember, we clearly identified that, okay, there was one instruction accessing the same memory address, another instruction accessing the same memory address, but this one took 8 cycles. Sorry, yeah, this one took 1 cycle, okay? So that means that one of these instructions hit the cache, and the time that it took to access the cache is the cache access latency. You see, it's right in front of you. The answer is always in front of you. You have to learn how to find it. That's the trick. Okay, I'm not going to solve it right now. I'm going to keep reading. I'm going to keep filling in the gaps in my mental image. What is the cache miss latency? Okay, yeah, so I was reading this question. What is the cache miss latency? This is quite similar. I just saw it, right? So if my cache hit latency was 1 cycle that I just saw, then the other one must be the cache miss, because that is what was loading the data in the cache. So that should be 8 cycles, as we saw in this table, in this execution diagram. This was a cache miss, and this was a cache hit. All right. What is the cache line size? The third question is, what is the cache line size? Interesting. Now, when you see cache line size, you should think about, how do I figure out the cache line size? I can figure out the cache line size by changing the address that I am accessing. But surprisingly, in the entire execution diagram that we saw, we never changed the address. So if you look clearly, you can see the stores and the loads happen all at R0. And the value of R0 is, let me zoom in. Right. If you look carefully, R0 value is what is being accessed in the memory, and R0 never changes. Okay, so I don't know yet. I would need to read the question once again to figure out what is the cache line size. Okay, well, that means my mental image is incomplete. All right, let's keep going. What is the number of entries in each reservation station? Now, do you remember the reservation stations that we saw? Yes. So these reservation stations are used to store the instruction before they're scheduled for execution on the ALU or the memory. What is the size of this reservation station? The size of this reservation station is the amount of instructions that are executing concurrently. What do I mean by concurrently? First of all, I hope you understand Tomasulo and you understand how we schedule on ALU and we schedule on memory. If you are not clear on that, I would be happy to explain it separately after we do the question. But yeah, you have to think about the size of the reservation station. You have to understand how many instructions are in flight or in execution at the same time. In the execution diagram that I see these two instructions. For instance, I see this branch and I see this mul. Now I know that branch and mul will both access the ALU. If you remember, we were clearly indicated that they access the branch and mul, and both of them, I see them concurrently being executed, right? So that gives me a hint that maybe they were both executed at the same time. And yeah, that could be a possible size for the reservation station. All right, let's keep going. How many ALUs does the processor have? Once again, how many ALUs, how many number of entries in the reservation station? All of these questions hint, because you can only execute 2 instructions in parallel when you have the resources to execute them in parallel. Okay, so either you would have reservation stations or either you would have multiple ALUs. So once again, you have to figure out which instructions are executing in parallel. And executing in parallel means they have the E stage going in parallel. Okay, and I see once again, these 2 instructions hint that they were executed in parallel because their E stages overlap to some extent. It doesn't matter that this instruction was killed. The fact that it was scheduled and it was in the ALUs means that the system has the capability to execute 2 instructions in parallel. Okay, all right. Things are sort of making sense, but still we are not done with the questions. Is the integer ALU pipeline? That's fairly simple. Pipelining means, does the ALU take more than 1 cycle to execute the instruction? Yes, I see this move instruction that takes 4 cycles. I see this multiply instruction that takes 3 cycles. I see this add instruction that takes 3 cycles. Of course, the ALU is pipeline. Okay. Yeah. Yes, exactly. Yes, you're right, but you break it down into smaller cycles so you can execute multiple instructions in parallel. You're right. Okay, maybe I missed that. I should have explained that. My bad. So Okay. I'll try to update the mental model for that. Let me keep going and let's discuss it afterwards if that's okay. Yeah. Thank you for the question. All right. Does the processor perform branch prediction? We saw that there are some instructions getting squashed, and we saw that these instructions were preceded by a branch instruction. That means that most likely the processor does perform branch prediction. Okay. And now we come to the last question. At which pipeline stage is the correct outcome of the branch evaluated? Now, at which outcome, when the correct outcome of the branch will be evaluated, that is when the next instructions will be squashed. So outcome evaluation implies that I know where this branch is going to go. And as soon as I know where this branch is going to go, I can decide if my earlier path was correct or not. That means it is the point at which the next instructions were killed. That is when the outcome of the branch was decided. We can see here that this branch outcome was decided at this right stage. And exactly at this stage, these two instructions were killed. Okay, so great. Yeah, we have gone through the entire question very carefully. We have built up a mental image of what we're going to do. And yeah, now we can just start filling in the answers. And it was, I hope it was very clear on what I was trying to do here and how to approach these type of questions. Okay, so what is the cache hit latency? Once again, let's take a look. We saw two load store instructions. Both of the instructions hit the same address. That is why I can infer something about their cache accesses. The first instruction took 8 cycles. The second instruction took 1 cycle. That means cache hit latency is 1 cycle. What is the cache miss latency? I saw that this instruction waited 8 cycles. So cache miss would be 8 cycles. What is the cache line size? In the mental image that we built, to infer the cache line size, you would need to change the address of the memory that you're looking at. We see that at any point in the program, we are always accessing R0. R0 is the memory target, and we never change the value of R0. R0 is not the destination for any of your ALU instructions. That means I cannot tell what is the size of the cache line. Now, one more way that I would like you to think about this, if you read it more carefully, right? So this is some more description that is put in the question. Now, description is not put in the question for filling up pages. Description is always put there to help you solve the question. Let's take a look at what this description says. This description says, using the information above, answer the following questions regarding the process design. Okay. If a question has more than one correct answer or a correct answer cannot be determined using the information provided, answer the question as specifically as possible. It is intentionally designed to be vague. Okay. Do not expect to find exact answers. All right. That gives me a hint that, okay, there might not be an exact answer. Use phrases such as at least or most and try to narrow down the answer. All right. If nothing can be inferred, write unknown as the answer. The fact that this statement is present in the description means that the authors intended some, not always, but usually some question as unknown. So it gives you a hint that one of these questions was designed to be unknown. And we see clearly that the cache line size is unknown. Okay. What is the number of entries in each reservation station? Now, let's take a look once again at the execution diagram. We saw this already. By the way, one more tip. Why am I doing the same question twice? Because these are numerical questions. In the exam, you are extremely likely to make a calculation mistake. By solving the same question twice, you are doing yourself a favor by eliminating the chances for any calculation mistakes. Okay? It's very easy to be in the pressure in the exam and see, oh, this is 7 and not 8. And then you'll write 7 and you'll lose your points. So yeah, this is one way that you can avoid, just solving it twice will cost you like 5 minutes, but it will make sure that the answer is correct. Coming back to the question asks, what is the number of entries in each reservation station? Now, we were thinking about, in our mental image, the number of entries in the reservation station can be inferred by the amount of instructions that are in the execution stage simultaneously. In our execution diagram, we see these two instructions have their execution stages overlapping to some extent. Okay. This one does not have the execution stage overlapping. Okay. This one also does not have. So these are the only two instructions which can give us hints about the number of reservation stations or the number of ALUs. Okay. Now we have narrowed down where we are supposed to look for the answers. Now these two questions are sort of similar. So in this case, either you can have two entries you can have two entries in this ALU reservation station, or you can have two ALUs. Okay, both of them are possible answers. Question asks, what is the number of entries in each reservation station? Once again, careful reading, each. Remember that we had two reservation stations. You need to answer what is the number of entries in the memory reservation station. Coming back to the concept, how do you determine the number of entries in the memory reservation station? You look for instructions which have the overlapping execution units, but unfortunately, I don't have any such instructions. Unfortunately, I saw that all of my load stores are preceded by other instructions, so it is very difficult to determine this. In this case, you can say that the number of entries in the reservation station for mul is unknown. All right, how many ALUs does the processor have? As we just deduced from these two instructions which were concurrently in flight, either we can have two reservation station entries or we can have two ALUs. So how many ALUs does the processor have? Potentially two ALUs. We don't know exactly for sure. We would need to see a larger history of execution to make an exact estimate. Finally, the next question is the integer ALU pipelined? Yes, the integer ALU is pipelined because we have these, the E2 stage. Once again, let's zoom into this part. Why do I say it is pipelined? First of all, this is a branch and this is a mul. And I know that the ALU, I apologize for the fast movement. Yeah. And I know that the ALU is responsible for executing the branch and the mul. And I see both of them in flight simultaneously at this point. That means, yes, the ALU is indeed pipelined because it is able to. Can we do it afterwards? Yes, right. So, yeah. I would be happy to help you get this concept right, but please let me finish this. All right, does the processor perform branch prediction? We saw clearly some instructions got squashed. Once again, the tip to remember, squashing means dynamic execution. Dynamic execution can come from load stores, branch predictors, load value predictors, some other arbiters, but usually it is branch predictors. So yes, we do perform branch prediction and our branch prediction went wrong. Yes. At which pipeline stage is the correct outcome of a branch evaluated? The concept associated with this question was the branch evaluation is committed at the W stage. And when I know that my branch is not going to be taken at the W stage, I will kill the subsequent instructions. The subsequent instructions that were preceding this, that were both killed, were killed immediately after the W stage. So at which pipeline stage is the correct outcome evaluated? That would be W stage. Okay. That sounds good. We just got 32 points. Perfect. Now let's take a look at how do I get the rest 18 points. Oh, I see this one more simple not simple, but okay, once again, don't panic, just relax. Read the instructions carefully. What is the program that is starting instructions that lead to the execution diagram shown in table 3? Fill in the blanks with the known instructions of the program and also show where and how many instructions are there in the program. The question asks us to read the execution diagram and try to predict what was the original program. Now, why can the program execution sequence change? The program execution sequence can always change because of branch prediction, because of function calls, because of changes in the instruction pointer. I see that there were no function calls in the execution history given to us. I see that there were no changes to the stack pointer or to an instruction pointer. The only confirmed change that I saw was this branch jump, which was wrong. So this gives me a hint that most likely this was the exact sequence of the program, with the exception of these two parts, with the exception of these instructions. These might be the tricky ones to get right, but otherwise, since I know that there was no change in the control flow, the control flow change can always be affected only via function calls or via stack pointer or via instruction pointer. I know that I can copy them directly to the answer. Okay, let's do that. So we have this move R0, 0x1000. Okay, then we have a load R1 to R0. All right. Then we have a branch if less than R1 . Okay, now at this point, I should try to take a look at the instruction semantics to figure out what could be wrong here, because I don't know what this branch does. I see a BL. This word means nothing to me until I read it. Let's take a look at the instruction semantics and what the instruction semantics say. The instruction semantics for the branch instruction says that a branch instruction that conditionally takes the path specified by the label LB1 if the content of register R1 is smaller than integer value 100. Okay, so branch if less than if R1 is less than 100 to LB1. This is interesting. Using the same semantics that we just saw, this instruction in the execution diagram says branch if R1 is less than 100 to LB1. All right, now I need to figure out where would LB1 go. Since we know that the branch was, the path that we took in the execution diagram was incorrect, that means at the end of the evaluation of the branch, we had to jump to LB1. Okay, that means that this LB1 label is where the program execution started after we squashed the instructions. Remember that we squashed these two instructions, and after that, this was the first instruction that executed to completion. This is most likely where the label LB1 exists. Once again, I'll repeat it just to make it very clear. The branch will go, the next instruction that is completed to execution after the branch, the correct address for the branch will be the instruction that will be committed. The first instruction after the BL that we see is committed is W. This one, this add. That is how I know what is the address of LB1. Okay, so this means that these two were on the path. These mul and these store instructions were on the path that was not taken. All right. So if I think of this, if I think of the C code for this binary stream, I would say this would be an if R1 less than 100. If this is less, then go to LB1, else to this mul and this store. Okay, so at this point, we also know that these two instructions were executed, but they were killed later. So in the stream, these two instructions should come after the branch. Now, that means that at this point, let's leave a little gap here, since this part is a little hazy. We don't know what exactly happened at this point, but I know for sure that these instructions were executed afterwards. So they must follow the path. Multiply R1, R1, #5. Okay. Store R0, R1. So we know that the processor went in this path and then realized, oh no, this branch is supposed to be taken. So I have to jump to LB1. So this would be LB1. And this is where the next instruction, this one would be put. This would be add R1, R0, R1. Okay. And store R0, R1. All right. We don't know which other instructions were here. So the reason I left these gaps is because these two parts are hazy. We don't know. So it might be possible that there were some more instructions here which did not enter the pipeline. Some more instructions here at this point which did not enter the pipeline. And yeah, we just don't know. So yeah, it's okay if you don't put this, but yeah, this is like the best guess that we can make for what happened. All right, so yeah, that brings me to an end to this question. Now, once again, I'll quickly repeat the tips. Take a deep breath. Read the questions carefully. Okay, read the questions first. Form a mental diagram so that you understand what's happening. An image really helps you visualize. If you can visualize it, then you can solve it. And then finally solve for answers. And yeah, questions are built to be solved. The answer is always in front of you. You just need to understand where to look for it. And yeah, I wish you all a very good luck. And now let's take the question that you had. Can you come again, please? Yes. Oh. It does not defeat it because your reservation station size might be limited. Yes, that is very much possible. So yes, you are absolutely right. You understand. So now I can see that you understand the concept of reservation station because you need a large reservation station to extract the parallelism that gives you performance improvement in out-of-order execution. If your reservation station size is 1, then yeah, just do it scalar. Just do it in order. You're absolutely right. Right. I think that is because you see the first instruction move, and BL are simultaneously in flight. So right. So okay, let's take a look at instruction 1. Instruction 1 completes execution at the 7th cycle. The commit happens at the 7th cycle. After that, I have a load instruction. The load instruction will go to a different reservation station. Remember that we had 2 reservation stations? 2 queues, basically. So the first queue has the move. The second queue has the load. The third instruction, BL, would go to the first queue. And at that point, the first queue gets full. And then you have the mull, which is also supposed to go to the ALU, but I cannot send it to the ALU queue because that queue is already full. Yes. Yeah, that's a good point. I need to take a look into it. Yeah, okay. I don't have an answer to that. At this point, in this question, this is the best I could come up with. But you're right. I see your point, and it should be shifted backwards. But yeah, I'm not fully sure why it did not go that way. Can any other TA help me with that?
And the second question concerning part B, it will also be very important to bring it to the environment that instructions need to be followed.
We don't know which way the branch predictor goes. That's like, so we sort of see, so the point of this question was that it was showing you that the branch predictor predicted wrong. And we ended up spending time wasting on instructions which did not matter. So the question sort of hints that, can you come again? Like, do you see my point? Can you come again? Yes. 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 You are right. You are right. And that is why I left this gap. But if the branch was predicted taken, then we would not squash it, right? So you got to decide one if it's taken or if it's not taken.
Then we go back to
Yes, yes. So see, the point is that in any case, let's think of this as the branch. This is the taken, this is the not taken, and this is the normal execution stream. Now, what's happening is that my branch predictor said something. Let's not get into the words taken, not taken. My branch predictor said something. Okay, predictor says 2x, I'm gonna do x. But then when the answer for the branch is available, when I know that the predictor was wrong, at this point, I have to get rid of what I did in this x. That means I have to, this is what is stated in the question as squashed. And then I have to do what was the right thing to do. So the right thing to do is what will hint you at LB1. That's a possibility, yes. But okay, this is once again, this is getting okay, I don't know how to say this correctly, but you are right. I understand your concern. You're thinking about edge cases, which is very good. It's not an edge case, but you need to solve this question and move on, right? You have 20 minutes. So this question is meant to be solved. I see that you're trying to dig deeper, but take what's written at face value. Because if the face value is wrong, then you can always appeal in the final exam. You could name that as LB2. So you can always switch the labels around, right? You could I could say that the one that was squashed was LB2 and the other one was LB1. You can always switch the label. You're basically asking that this could be LB1, but my point is that this could also be LB2. I appreciate your questions. They make sense, but yeah, you need to finish it within 20 minutes. Take it at face value. Think of edge cases when they explicitly ask you to think of edge cases. Usually they will tell you. Yeah, I hope this was clear, and let me know if there are any questions.
Hello, everyone. Now we are going to talk about GPUs and Cindy. This is a type of question that for sure, well, better word. For sure, you're already familiar with this type of question because we have it frequently in our exams, but still it's good to solve it and it's good to go over the question completely and comment a little bit about it. So this is question 8, GPUs and SIMD. The question says, we define the SIMD utilization of a program that runs on a GPU as a fraction of SIMD lanes that are kept busy with active threads during the run of a program. As we saw in lecture and practice exercises, the SIMD utilization of a program is computed across the complete run of the program. The following code segment is run on a GPU. A warp in the GPU consists of 64 threads. That's important. And there are 64 SIMD lanes in the GPU. So what that essentially means is that when one warp executes one instruction, the instruction takes one cycle. Remember that in the GPU lectures, we covered as well, the cases where the warp size was greater than the number of lanes. And in that case, we would need to schedule the instruction across several cycles. But here is just one cycle. Each thread executes a single instruction of the shown, a single iteration of the shown loop. That's also important as well. In total, as you'll see here, there are 4,096 iterations. So what that means is that we are going to need in total 4,096 threads. Assume that the data values of arrays A and B are already in vector registers so that there are no loads and stores in this program. So for example, here you have this instruction 2. As you see, there are indeed 2 memory accesses, 2 reads, right? A of I and C of I, and then finally one write, but we consider that this is a single instruction. We consider that the values that we are operands, input and output operands that we are going to use in this question are already in registers. So we ignore those accesses to global memory of the GPU. Both A and B are arrays of integers. Hint, notice that there are 6 instructions in each thread, right? Well, they are clearly marked here. So again, the same for the if statements here. We are considering just a single instruction for each of the if statements. Okay, so let's, also very quickly, as I mentioned earlier, there are 4,096 iterations here, so that's the number of threads that we are going to need. And then in the body of the for loop, we have 2 if statements. One of them is checking if B of I is lower than 8,888. And the other one is checks if that value is greater than, right? So observe that is lower or greater, right? Now the exam says, the question says, please answer the following 4 questions. So let's go one by one. First one is pretty easy. We always have this question in this type of GPU and SIMD question, and it's a kind of 3 points. The only thing that should be clear for you is that the total number of iterations is going to be the total number of threads that we need, and what's the number of threads per warp, right? And that's information that the question gives us. So what's the total number of warps is equal to the total number of threads divided by the number of threads per warp. So this is 4,096 is 2 to the 12. 64 is the number of threads per warp. That's 2 to the 6. So this means that the result is 2 to the 6. So in total, we need 64 warps to execute this code. Okay. I guess no questions here. Anyway, feel free to raise your hand if you have any question. Okay, second one, it says we measure the SIMD utilization for this program with one input set. We find that it is 134 over 320. What can you say about arrays A, B, and C? Be precise and look at the if branch is the hint that we are giving here. So, so we have three arrays, right? And we are being asked about three arrays, A, B, and C. So if we observe the code and we observe the if statements, we see that the only important, so the only array that is important to make control flow decisions is array B, right? So there is no impact of the values in arrays A and C that affects the execution of this program, right? So what can we say about A and C? We can say nothing. We cannot say anything about them, right? Because the execution of the program and the total SIMD utilization is not going to, is not related to the contents of A and C. But how about B? So clearly, the values in B are important, right? Because it's, so here in the instruction 1, we check if the value in B is less than something. In instruction 5, we check if it's greater than something, right? So let's think about how someone who has calculated the SIMD utilization for specific values in array B has, let's say, reason about the calculation. We know that the SIMD utilization is equal to 134 over 320, right? And here we can probably do different things. We can reason here in different ways, but I'm going to take advantage about the take advantage of the fact that I'm giving this number, right? And if I see this fraction here, I see that in the denominator I have 320. And 320 is equal to 5 times 64, right? And remember as well that when I calculate the SIMD utilization, what I have in the numerator is the number of instructions that are really executed, or the number of operations that are really executed, which means that, for example, in one of these instructions is only executed by one thread in one warp, then the value here in the numerator is 1. But if I have 64 threads in each warp, the maximum number of operations per warp and per instruction would be 64, right? So 320 is 5 times 64. I'm going to assume here as well that all warps are doing exactly the same. That's usually the normal thing in these kind of exercises. And I know that 5 instructions are being executed in total, right? And the only way to execute 5 instructions in this code is by having threads that go through the body of the first if statement, right? And then these, or some of the threads will, or actually all the threads will also execute this instruction 5, and none of them will execute this instruction 6. That's the only way of executing only 5 instructions in this code. So now we know that a certain number of threads executed instructions 1 to 5, and no threads executed instruction 6. Are there any questions here? Okay. Now I can also see that all threads, all 64 threads of the warp execute this one and this one, right? Because before deciding if you go to the body of the if statement or not, you have to evaluate the condition, right? So everyone does that. So this means that 2 instructions are executed by the 64 threads of the warp, right? And then there are 3 more instructions 2, 3, and 4 that are only executed by some threads. I know that it's not all of them, because if it was all of them, then here I would have 320 as well, right? But it's not 320. So only part of the threads, let's say, let's call this number T, is going to execute these 3 instructions. You see it? So from here, you will obtain that T is equal to threads. And what this means is that there are 2 every 64 values, actually consecutive values, of B are less than this number. The rest are exactly the number. Is it clear? No questions? Okay, good. So then for the rest of the question, we are going to reason in a very similar way, right? So the next one says, let's put it like this. Okay, the next one says, part C says, what needs to be true about array B to achieve 100% utilization? Show your work, be precise and complete. And it's important to be complete, right? So you may be able to come up with more than one possible solution. And here we are asking you to be complete, which means that you have to give us all the solutions. The warp scheduler does not issue instructions where no threads are active. This is something that we assumed earlier as well. So there are 3 possible answers indeed. But the very first thing that is important to achieve 100% utilization is that all threads in the warp do exactly the same thing all the time, right? There's no divergence. And there are 3 possible ways of not having divergence in this code. The first way is that all threads only execute this if, including the body, plus instruction 5. The second possibility is that all of them execute this instruction and then these 2 instructions, but not the 3 in the body. And the last possibility is that all 64 threads in each warp only execute this instruction and this instruction, but none of the bodies, because the values in B are all equal to 8888. Right? So these are the 3 possibilities. The first one is all 64 consecutive values of B are equal these, or all of them are less than this number, or all of them are greater than this number. Make sense? Of course, if you check the code, you'll see that for each of these 3 possibilities, the total number of instructions is different. The total number of executed instructions is different, but we are not measuring the number of instructions. We are measuring the utilization, right? And we average the utilization over the entire execution of the program. Okay, yeah, next question is, what is the minimum possible SIMD utilization of this program? So we already know what's the maximum is 100. What's the minimum? But before, you know, like, I mean, in order to do part C, you have to do part E first, right? Because in part E, we were actually asking about what needs to be true about array B to achieve the minimum possible SIMD utilization. Show your work. Please cover all cases in your answer in case there are more than one case. We only came up with a single case. And in this case, what happens is that we have as much divergence as possible. That's the case where the SIMD utilization is the minimum, right? And we already know that in this code, there are 2 instructions that are always executed by all 64 threads. the two instructions are instruction 1 and instruction 5. Threads always evaluate the condition. Then what is the maximum divergence that we can achieve for the rest of instructions? For these 3 and for this 1, for this like this body here and for this body here, the highest, the maximum divergence happens when only one thread in the warp executes the corresponding instruction, right? So here, what for the minimum, we are assuming, or we are guessing that only one thread executes these 3 instructions, another one thread executes this instruction 6, and the rest of threads simply don't execute more instructions because their values are equal to 8,888, right? So, so then, as I said, every 64 consecutive values of B, one is less than 62 are equal, and one is greater than this number. And now here I'm going to make use of this space, even though the answer, I'm going to calculate the answer of to part B. So here I calculate the SIMD utilization as, what's the total number of instructions? Remember, that is 6. 6 times 64. Now remember that there are 2 instructions that are always executed by all threads, no possible divergence there. So it's 2 times 64. And now there is only one thread that executes instructions 2 to 4. So this is 3 times 1. And then there is only one thread that executes instruction 6. So this is 1 times 1. So if you calculate this, you will obtain 132 over 384. So that's actually the solution to this part. Is it clear? So when you try to calculate what's the minimum utilization, always try to think, it's kind of a hint, is always try to think about how to involve many instructions in the calculation, and then for each of the instructions, try to minimize utilization, right? So that's what we are doing here, is because in total there are 6 instructions, I want at least one thread to execute each of the 6 instructions. And this way, the number in the denominator will be larger and the total utilization goes down. Okay? Let me know if there are any questions. No? Okay. Yeah, thank you very much for your attention, and I wish you good luck for the exam. And yeah, take advantage of the forum as well, as Mohammed said. Who's next? Hassan? I think Hassan is online. Hello, Hassan.
Hello. Yeah, I can go next. I think according to the list, Haosung is next, but yeah, I guess it's better for me if I go next.
Okay. It's not? Okay, okay, go ahead.
Okay, so just a question, can you hear me well? Because I guess like previously there was a problem with like the audio.
Yeah, we can hear you well, Hassan.
Okay, you can understand what is, okay, great. Okay, I will share my own screen. Okay, so the next question is on branch prediction. I will very quickly read the question. So here we have a processor that implements an in-order pipeline with 15 stages. Each stage completes in a single cycle. The pipeline stalls on a conditional branch instruction until the condition is evaluated, but we don't know at which stage the branch condition is evaluated. And we need to answer the following questions. In part A, there's a program with 2,500 dynamic instructions that complete executing in this many cycles on this processor. So if 500 of those instructions are conditional branches, at the end of which pipeline stage are the branch instructions resolved? Okay, so yeah, we basically need to find that in this part. And we assume that the pipeline does not stall for any other reason than conditional branches, and examples are data dependencies during the execution of the program. Okay, so like the only reason for a stall in the pipeline are the conditional branches. Okay, so how do we calculate the cycles, right, for a given program? It's basically, so let me, okay, write it here. So we can calculate the total number of cycles with this simple formula, right? So like first is the number of pipeline stages. So assume you have only one instruction that you need to execute in this processor, right? So it will execute exactly in 15 cycles because like the instructions will go through every of the pipeline stages. If you have two instructions, then these two instructions will be executed in 15 plus 1 cycles, right? So, and we can generalize this as, so given we have like, a program with n instructions, that program will execute in 15 plus n minus 1. Okay, so we do -1 because the first instruction is included in these 15 cycles, right? And then we assume n is the total number of instructions that are in the program to execute. Okay, so here we can replace n with the number of dynamic instructions given in this part A, which is 2,500. Yeah, so this is basically the formula that we will use. Plus, we need to account for the bubbles introduced by waiting for the branch conditions to be resolved. We have 500 conditional branches, and then we don't know exactly how many bubbles they will introduce. And for now, like assume every branch instruction is introducing X bubbles, right? And then we have 500 of these instructions. So we can here replace the total cycles with the given program execution time, which is 4,514 14 cycles. And yeah, so here, when you do the math, here X should be equal to 4. Okay, and 4 is, according to this equation, the number of bubbles, right? So here, be careful. The question is asking at the end of the which pipeline stage the branch instructions are resolved. And then the answer should be at the end of the 5th stage, right? Because it introduces 4 bubbles. So assume like the so the easiest way to like check this, or whether it should be 4 or 5, is to like think about the simplest case where the branches are resolved in the 1st stage, right? So like if the branches are somehow resolved in the 5th stage, then there will be no bubbles, right? So like in the 1st stage, 0 bubbles. So then basically, yeah, the number of bubbles caused by the branch instructions are the stage at which the branch is resolved -1. Okay, and yeah, this was part A. Yeah, I will clear this when I scroll down. Okay, so in the second part, we have a new higher performance version of the previous processor. that uses a mysterious branch prediction mechanism. And with this new processor, updated processor, the following code here executes in 136 cycles. Okay, so here it says like everything else is the same about the processor. So we found that the branch conditional branches are resolved at the 5th stage. So we can use that information in this question. Okay, the first question is, how many instructions will be executed when running this piece of code, and show your work? So let's first try to understand what's happening here. So we have a register R1, which is initially 0. So this first instruction just writes 0 to R1. And then there's a branch that will jump to last when R1 is equal to 5. So initially R1 is not equal to 5, it is 0. So we move on to the add instruction. The add instruction adds 1 to R1, and then we move to the next instruction. Here we have like a second register, R2, which is 0. Okay, so we continue moving on inside this part that starts with the loop 2 label. And here again, we have like branch equal instruction. And here R2 is initially 0 and compares it to 5, which is like R2 is not 5. Then we don't jump to loop 1, which is the beginning here. Okay, instead, the program continues and R2 is incremented and we jump back to, so this is unconditional branch, right? So like this is just direct branch as annotated here to loop 2. Okay, so like when you think about it here, what happens is this part is executed 5 times. This is because like we start with R2 at 0, and then we don't take the branch for when R2 is 0, 1, 2, 3, and 4. And when R2 is 5, we take this branch and jump back to loop 1. Okay, so this piece, this part of the code is executed, like all these 3 instructions are executed 5 times. And then we exit this part by executing this branch equal instruction 1 more time, right? When it is finally taken. Okay, so the same logic actually applies to this loop 1 part. So when you think about it, it's exactly the same thing as loop 2, but with the difference that like after going through this part once, we execute loop 2 5 times, 5 plus 1 times, let's say. Well, 5 times the 3 instructions and 1 more time the branch equal instruction, to be more precise. Okay, and but like these 3 instructions also execute 5 times, as in the loop below. And when this branch equal is taken, this is the last iteration of the loop. We exit loop 1 and then move to the last instruction here, which just assigns 1 to R1. Okay, so let me complete here the execution counts of each of these static instructions. Yeah, so, okay. So basically, yeah, this is what the program does. And then if you calculate the total number of instructions executed here, it will be 1. 1 is this first instruction here, moving 0 to R1. And then this part is a bit tricky, right? So 5 times we will enter loop 2. And loop 2 is consisting of like 5 times 3 instructions plus 1. Okay, so 5 times we will go from loop 1 to loop 2, which will be like 16 instructions here in total. And then 5 times we will execute these 3 instructions of loop 1. And I will do plus 1 for this for the last execution of this branch over here. which will make the program jump to the last instruction. Okay, and I will do +1 one more time. And then here, if you do the math, this should be equal to 3 plus 5 by 16 plus 15. Okay, and then this is 80, 95, 97. Oh, sorry, 98. Okay, so this is the total number of instructions we have. If you scroll down to the second question, it says how many of the instructions are conditional branch instructions? Show your work. So calculating that is now much simpler because we know what the program does. So basically, instead of counting all instructions, we will only count the branch equal instructions. And yeah, so in the first part, in loop 1 part, we execute the branch equal instruction 5 plus 1 times, right? So like 5 times when the branch is not taken and once when it is taken. And for loop 2, the branch equal instruction will be executed. So you'll enter loop 2 5 times, and every time we enter it, the branch equal instruction will be executed 5 plus 1 times. Okay, so 6 times in total. Okay, I forgot to put plus here. And here, when we do the math, here the answer should be 36. Okay, so we have 36 conditional branches executed in this program. Okay, and these are the answers to the first 2 questions. Let me see. Okay, so I won't like remove these calculations for now. Let's keep them and let's quickly read this part C. Based on the given information, determine which of the following branch prediction mechanisms could be the mysterious branch predictor implemented in the new version of the processor. For each branch prediction mechanism below, you should circle the configuration parameters that makes it match the performance of the mysterious branch predictor. Okay, so we need to understand a bit better like what this mysterious branch predictor is doing, right? So far, these first two questions did not reveal any information about the branch predictor. But let's reveal some information by calculating how many mispredictions the branch predictor did, such that the execution of this program resulted in 136 cycles. Okay, so it's the first formula that we use in part A. We have 98 instructions in total, right? So the total cycles for this processor will be equal to 15 plus 98 minus 1 plus we know that every branch misprediction will result in 4 bubbles. Then we do 4 multiplied by n, where n is the number of mispredictions. Okay, so here again, 15 is the number of stages we have in the pipeline. So initially we fill up the pipeline and then we retire 1 instruction at the end. And then we have 98 minus 1 more instructions, plus we add the total number of mispredictions and multiply by 4, which is the number of bubbles. Okay, and then here we can replace the total cycles with 136, which is given in the question. And then do the math, right? So like this is 112 plus 4 times n. And then from here we find 24 equal to 4 times n. And from here n equals 6. Okay, so it's 6 mispredictions. So whatever this mysterious branch predictor is, it should result in exactly 6 mispredictions in order to achieve 136 cycles of execution time for this given program. Okay, Okay, 6 mispredictions. This is what we need to keep in mind for the rest of the question. Okay, I will clear all the drawings now. And let's also quickly analyze here how the branch outcome, what are the branch outcomes. So for the first branch, we know that it will execute 6 times in total, right? And the first 5 times, it will be not taken. And then the last time it will be taken when we jump to the last instruction. And for the second branch equal instruction, it will have the same behavior, right? So it will be not taken 5 times, and 6th time it's executed, it will be taken. So here, one thing you need to keep in mind is that the order of these branches are executed. So here, once we execute branch, the first branch once, and it is not taken, this second branch will go through all of these outcomes, right? So for each single execution of the first branch, we will execute the second branch 6 times, and then the outcomes of these 6 executions will be 5 times not taken, followed by 1 time taken. Okay, cool. So like these are the branch outcomes basically that we will need to consider in the rest of the question. And now it is good that these text moves as I scroll, because like we can refer to these outcomes as we answer the questions. Okay, could this be the mysterious branch predictor? And the example is a static branch predictor. Okay, and then here we have 2 options, either predicting as always taken or predicting as always not taken. So if you predict as always taken, as you can see, like we'll make many mispredictions, right? So like the first, okay, let me scroll down a little bit. Okay, so the first branch here will be mispredicted, and then the next branches over here that should be not taken will also be mispredicted, right? So like during the first iteration, we like mispredicted 6 times already, and then only the last branch here will be correctly predicted as taken. Okay, and then the next time, like we execute this first branch, we'll have 7 mispredictions, which exceed the target of 6 mispredictions, right? So the static predictor is not always taken, right? So, or the mysterious branch predictor is not statically always taken. You know that for sure. Okay, but what if we predict always not taken? Well, then we will correctly predict for the first, oops, that's not what I meant. Yeah, so like those not taken branches will be always correctly predicted. And then we will do 1 misprediction here for this taken branch. And then we will do this 5 times, right? Because like we will enter this loop 2, if you remember, 5 times after every execution of this non-taken branch of the first branch. Okay, so from here we have 5 mispredictions. And for the first branch, the branch predictor will do 1 more misprediction for the last iteration where the branch is taken. And in total, we will have 6 mispredictions. Okay, that's good. So this is exactly what we are looking for. And then here we can say that, yeah, so the mysterious branch predictor could be the static branch predictor with the always not taken option. So here the answer is yes. And the option that satisfies this, the given requirements is always not taken. Okay, oops. Okay, anyway, I'm not gonna draw anymore because it's sort of hard to remove. Okay, and then the next part is, so it's the same thing, but here we are going over like different branch predictors. Could this be the last time branch predictor? Yeah, so here again, we need to evaluate each of these options that we have. So last time branch predictor, what it does is it predicts the last outcome, basically, right? So like if the previous branch was not taken, this branch predictor will predict the next branch as not taken. Okay, and then here we have two options. The initial prediction direction can be either taken or not taken. This is only for the first branch. And then we can store this information locally or globally. So local means that every branch instruction has its own like one level of history, right? So like we treat the previous outcome separately for every branch instruction by using the program counter to differentiate the two instructions. Or the second option is like to use a global last time branch predictor, where the branch history is shared across all the branches. Okay, so just for the sake of time, I guess I will not go over these one by one, but here the answer is that it's like no matter what options here you take, the branch predictor will always make more than 6 mispredictions. And yeah, so here the answer is basically no, this cannot be the mysterious branch predictor. Okay, so if you understood how the last time branch predictor worked, I think it should be very easy to go over these outcomes and then see that this cannot be the mysterious branch predictor. Okay, maybe I will go over one example. So assume that the initial direction is not taken, and then we use local branch predictor. Okay, so like when we look at each branch individually with not taken, the first outcome will be correct. The first outcome will be correctly predicted. So not taken, not taken, not taken, and then so basically the first, like all not takens will be correctly predicted in this case, and the only misprediction will be in this last T. Okay, so here we have one misprediction for the first branch. And for the second branch, again, the same thing, except like we'll have one misprediction at the end for this taken. And then the next time, remember that we execute this sequence 5 times, right? For the second branch. The next time we like return back to the first not taken, it will be mispredicted because the last time branch predictor predicted, or the outcome was taken, and then the last time branch predictor will also predict this not taken, the actual outcome not taken branch as taken. So it will make one more misprediction, right? So for the first iteration, it will make one misprediction, and for the every other iteration, we will have 2 mispredictions, and it will make 2 mispredictions for the next 4 iterations, or I should say, next 4 times this loop 2 is entered. Okay, and in total here for this loop 2, we make 9 mispredictions, which is more than 6. Plus we had 1 misprediction for the first branch. Okay, so this was just an example of these cases where we assume the branch predictor is configured as initially not taken with local with local history last time branch prediction. Okay, moving on. The next branch predictor is backward taken, forward not taken. So this is simple. Could this be the mysterious branch predictor? So let's look at whether these branches are backward or forward branches. So this branch equal jumps to last, right? So this is a forward branch. But the second branch in loop 2 goes back to loop 1. So this is backwards taken. Okay. And then this predictor will predict backwards as taken and forwards as not taken. Okay, so here for the first branch, then we will have, again, so this is a forward branch and it will be predicted as none taken, not taken, and 5 times it will be predicted correctly, and the last time it will be predicted incorrectly. So we have one misprediction for the first branch. And for the second branch, this is a backward branch, and it is not taken 5 times. So all these 5 times not taken will be mispredicted, and only the taken paths will be correctly predicted. So we have 5 times misprediction. Okay, so here, don't immediately jump into the conclusion that we have 6 mispredictions in total, because remember we execute these this sequence of 5 non-takens and 1 takens for the second branch 5 times in total, right? So like here, the total mispredictions for the second branch will be 5 times 5, which is 25 plus 1. Okay, so then backward taken, forward not taken cannot be the mysterious branch predictor because we make 26 mispredictions in total. Okay, and then this is the last part. This is a 2-bit counter-based prediction. Okay, just to remind you how this works. So we have like a 2-bit history, so this again can be either local, like per branch instruction, or global, shared across branch instructions. And how this works is initially we have some state, some starting state, either 0, 0, or one of these 4 cases listed here. And so every time like an outcome of the branch is evaluated, the counter is incremented or decremented. Right? So for example, assume we are at 0, 0 and strongly not taken case. If the actual branch outcome is taken, then the counter will be incremented to 0, 1. And from that point on, the prediction will still be weakly not taken. But once we encounter one more taken branch, the counter will be incremented 1 more time to 1, 0. And from that point on, the branch predictor will start predicting the outcomes as taken. Right? And then depending on whether the actual outcome of the future branches is taken or not taken, we'll keep incrementing or decrementing the counter and making predictions based on the current value of the 2-bit counter-based branch predictor. Okay, so here are some configurations that work actually that result in 6 mispredictions. And these are, so just like based on the solution that we provided for this question, these are yes, local or global doesn't matter, and these 2 cases where we start from strongly not taken or weakly not taken. Okay, all these configurations result in exactly 6 mispredictions. So as an example, I can run one example. So this time, let's choose the global mispredictor, not local, and start with, let's say, strongly not taken case. Okay, so this should result in exactly 6 mispredictions. Okay, so we take this as a starting point and a global predictor. Okay, so here we need to go over the branches one by one. The first branch is not taken. This will be correctly predicted, and then the counter remains at 0, 0, and we don't have misprediction. Then we enter this sequence of 4, 5 non-takens and 1 taken. All non-takens will be predicted correctly, and then will remain at 0, 0. And then this taken branch will be mispredicted, and the counter will be updated to 1, 0. Afterwards, we go to this branch. So I'm just ordering the following the program order, right? And then here we will have correct prediction. Although the counter is at 1, 0, remember this is a weakly not taken case. and the prediction will be still not taken. And then the counter will be updated to 0, 0 again after because the outcome of this branch will be actually not taken. And then, yeah, so here we had one misprediction, remember, for the first execution of this sequence of the second branch. And then when we enter the sequence one more time, we'll have one more misprediction. Okay, so I guess you see the pattern here. Every time we enter this the sequence of 5 non-takens and 1 taken for the second branch, we'll have one misprediction. And remember, we do this 5 times, so we'll have 5 mispredictions. And then, yeah, so we go over these branches, non-taken branches, one by one. And then finally, when we are here at the final instance of this branch, which is taken, we will again mispredict, because like when we leave this sequence for the second branch, remember we leave it when the counter is at 1, 0, which predicts this taken branch as not taken and gets updated to 1, 0, right? But the although we get updated later to weekly taken state, that is before we make the misprediction before we actually do that evaluation, right? So we get +1 misprediction from this first branch. And in total, we get 6 mispredictions, which is the number we are looking for to complete the program at the target 136 cycles. Okay, so basically for the options that are marked initially, like no matter whether you start at 0, 0 or 1, 0 weekly taken cases, or whether you use local or global branch predictor, it doesn't matter. For all these, the branch predictor will make exactly 6 mispredictions. Okay, are there any questions or any cases in particular that you want me to evaluate here as an example? Yeah, if not, I guess we are done with this question. So just let me check. Yes, this was the last part of it. Okay, thanks and have a nice weekend.
Okay, thanks a lot, Hassan. I think we're good. So, do I need to do anything on the computer also, or to show it? I am sharing the content from the second camera. Is that correct, or? Yeah, super. And can you hear me? Or yeah, okay, I guess so. Awesome. So well done on sticking it out. We only have one more question to go. This question is on VLIW, so very long instruction words. Let's go through the question first to see what we're dealing with. So we were told to consider a VLIW CPU that uses the long instruction format shown in table 4. This is table 4, and so we see that we have 4 slots for short instructions in each of these long instructions. So that's what they tell us next. Each long instruction is composed of 4 short instructions. However, note that there are restrictions on which type of instructions may go in which of the 4 slots. So as table 4 tells us here, the first slot can only contain memory instructions, the second one integer instructions, control instructions, and float instructions, respectively, for the third and fourth slots for short instructions. Then we have table 5. Table 5 provides a detailed description of the available short instructions and the total execution latency of each of them. Each short instruction execution unit is fully pipelined. This will be important, so don't forget this detail. And its result is available on the cycle given by the latency. What that means is, for example, for a control instruction, its results, if any, are made available for other instructions to use in the next cycle. Let's take a look here at the category control in table 5. We see that the corresponding latency is 1. So what that means is we issue the control instruction, and then the result is going to be available right after, in the very next instruction. So the information that we need to get from this table 5 is that we have one type of control instruction, which is the branch the branch if equal instruction. We have a load instruction, which has a latency of 3 cycles. We have an integer add and a floating point add instruction also. These should be very familiar. They follow syntax analogous to MIPS. So just keep these in the back of your mind. We'll come back to them as soon as we need them. So then we are given another table, this time with a piece of code. Unfortunately, you are going to be the compiler. So you know that this is the code that was generated from some application. However, unfortunately, this code contains a sequence of short instructions. So we cannot directly input these short instructions into the VLIW instructions, and that's going to be your job for today. So here we have table 6, which you can see is the proposed code for calculating the results of the next Swiss referendum. We're not really concerned about that, but our task is going to be to map each of these from 1 to 12 into basically the instructions that are scheduled in the VLAW machine. However, before we get into that, we have a warm-up question. So this warm-up question asks us, which of the following are goals of VLIW CPU design? And they ask us to circle all that apply. The options here are simplify code compilation, simplify application development, reduce overall hardware complexity, simplify hardware inter-instruction dependence checking, and reduce processor fetch width. Before we think about this, I'm going to quickly borrow from some of Professor Mutlu's slides. This is where the concept of VLIW was introduced. I just want to call your attention to a couple of sentences here, which I think will make it very, very easy to answer this question. First, the idea behind VLIW machines is that the compiler should find independent instructions and statically schedule, meaning packing or bundling, these independent instructions into a single VLIW instruction. Crucially here, this is the role of the compiler. And then also this first point here, a very long instruction word consists of multiple independent instructions packed together by the compiler. I'm just going to quickly scroll up here also. Yes, so a couple of slides back, we also have these important sentences. Hardware fetches and executes, the hardware fetches and executes the instructions in the bundle concurrently. And crucially also, there is no need for hardware dependency checking. Keep in mind, this is because the compiler itself is taking care of this for you. So there is no dependency checking on the hardware between concurrently fetched instructions in the VLIW model. So with this in mind, I think we can come back to our warm-up question here. Is the code compilation any simpler? Not really, right? This is not true. In fact, now there is added complexity because we need to take care to find these instructions that can be bundled into a single instruction. Is application development easier? Also not necessarily, right? On the one hand, there isn't even that much of an influence. This affects the compilation process, not so much the application development process. But if anything, it would become more complex because we need to take the microarchitecture into account when scheduling instructions. However, and this should be very, very clear from what we've just read, it does reduce overall hardware complexity. So this one is correct. And it does so, actually, the fourth option here helps us. It simplifies hardware inter-instruction dependence checking. We don't need to check for these dependencies between different instructions. We just need to execute them as they were scheduled, right? So it also simplifies the hardware inter-instruction dependence checking. Does it reduce the processor fetch width? Not at all. In fact, the opposite, right? The fetch width becomes wider, right? We fetch more let's say bytes with each instruction that we process, right? So this fifth option is also not true. So the answer here for part A is sentences 3 and 4. Now, we move on to part B. Now our task is to determine the optimal VLIW scheduling of the short instructions by hand. So we want to fill in this table that I briefly showed you before with the highest performance, that is the fewest number of instruction cycles, instruction sequence that may be directly input into the VLIW CPU and have the same functionality as the code in table 6. So we're going to have to basically keep these two things on, on our brain's RAM. We're going to need to keep this code that we want to map in mind. We're going to need to keep the latency of each of the operations in mind, and we're going to need to basically schedule them as we can, with the goal of minimizing latency. Or rather with the goal of maximizing performance, which is what the question states. Okay, so where possible, you may write instruction IDs, which is what I'm going to do for the sake of simplicity. Notice that each of the instructions here is numbered, so for the sake of simplicity, I'm just going to resort to using these numbers in this table. And we can also leave any NOP instructions. Note it's likely that there will be quite a few NOP instructions because we're not going to pack the entire table. And we can leave those as blank slots. Consider only one loop iteration, including the back instruction. Ignore initialization and any cross-iteration optimizations, for example, loop and rolling. As a brief side note, loop and rolling is very commonly used optimization technique, especially in these VLIW contexts. So good for you to know, but not relevant for this question. They ask us explicitly not to consider that, and also not to optimize the code by removing or changing existing instructions. So let's start. Oh, by the way, we also have a hint down here that the entire thing should not require more than 20 cycles. I don't think we're going to have that problem. So let's start at the beginning, which is, I think, when we're giving a sequence such as this, I think it's a good idea to start from the top and to follow the instructions sequentially, because this will also make it very clear where the dependencies arise, basically. So the very first instruction is a load instruction. And because it is the first instruction and we were asked to ignore anything that came before the execution of this code, obviously there is no dependency here. So the takeaway is that we can just schedule it as soon as possible, right? So now I come back to the table here, and of course, we know that the load instructions are memory instructions, and they have a latency of 3 cycles. So here, on the first cycle, I can place my first instruction. As I said, I'm just going to use the numbers here. Afterwards, or maybe concurrently, I can also show you the solutions sheet, which I have here, which is prettier. But for simplicity and also to help me with annotating some things, I'm just going to use the instruction numbers here. Okay, we go back to our sequence of short instructions, and the second one is also a load. What does this load depend on? It depends on the value of R1, and then it loads whatever is stored in the memory address stored in R1 into the register R1. There's no dependency. Again, so what that means is we can just come back here into the table and just schedule the second instruction right after the first one. Why can we do this? Notice that although the latency of the memory, or in this case of each memory operation, is 3 cycles, we are also told this thing that I underlined here, so that the execution is fully pipelined. What that means is, if I look at this first load starts in cycle 1 and is going to take a total of 3 cycles to become available, right? So I can use the value that I loaded in the first cycle at the earliest in cycle 4. However, because it's because the functional units are pipelined, I can start a second load while the first one is still ongoing, right? So what that means is I can begin this second load here in the second cycle. Great. So the next instruction up is this integer add. Now, this integer add takes in 2 arguments, R0 and R1. And those are the values that we're loading in these first 2 instructions. The issue now is that these are not immediately available. In fact, they will only become available as I was just saying, the value that we're loading in the first instruction, because this is a load instruction, becomes available in cycle 4, and the available for use in cycle 4, and the one in the second instruction becomes available for use in cycle 5. And because the two values that we're loading are the values that we want to use, right? What that means is that the earliest that we can schedule this third instruction is precisely cycle 5, right? When the second load becomes available. Awesome. Let's look at the next instruction. We have a floating point add now. This one requires the values of R0 and R4. So R0 is loaded in the first instruction. I've already said it, I think 3 times now. That becomes available in cycle 4. However, this value, the value of R4, only becomes available after this IAD completes. How long does the IAD take to complete? We scroll back up to the table and we see that the latency in cycles for these instructions is 2 cycles. So what that means is this integer add that we started in cycle 5 becomes available for use in cycle 7, right? 5 is the first cycle, 6 is the second cycle, and then the result is available for use in cycle 7. And I want to be really sure that I don't screw up. But so far, so good. What this means is we can scroll here to the right all the way to our float column, right? Because we'll remember the instruction that we want to do is a floating point add, and that can be scheduled as soon as this integer addition. Let me scroll. Zoom out a little bit. As soon as this integer addition, the result of this integer addition becomes available. And that happens in cycle 7. So here we can go to cycle 7 and we can store our 4th instruction. Great. So then we have another couple of load instructions. Note that these load instructions, the first one of them, requires the value R2. There is no prior dependency with any of the previous instructions. So this can, in principle, be scheduled as soon as possible. And however, for this second load word here, so the one at index 6, we do have a dependency on R0. The most recent instruction to modify R0 was the first instruction with a load. And we, again, need to remember that this has a latency of 3 cycles. So we want to schedule instructions 5 and 6. As I said, for the first one, not a problem. We can just schedule as soon as possible, right? The earliest slots that is available in the memory column is this cycle here, right? And then for this one, for instruction 6, we want the value of R0 to be the value that we load in the first cycle. How long does that take to be available? It takes 3 cycles, right? So this value becomes available here. That's very good news for us, right? Because what that means is, in this cycle, I can already schedule this instruction, right? Maybe now is a good time to revert back to this. This is the solutions, which with much prettier font type than what I can do. And so basically what you see here is that these 5th and 6th instructions can be scheduled here right next to each other. The R0 that we load from the first one is then used to basically for in this 4th cycle for the 6th instruction. Great. Now we have a bunch of arithmetic operations that we want to take care of. We have a floating point add here. This one requires the values in R1 and R6. Let's see. So R6 was last modified by this load here, and R1 by this load here. So essentially, we look at the latest load. The latest load here started at cycle. So this is instruction 5. We come back here. This is instruction 5, started here, and it's going to take 3 cycles to become available. So what that means is, by cycle 5, by the end of cycle 5, we have all that we need for this floating point addition. Since by cycle 5, the value of R6 becomes known, and the value of R1 was already known from before, okay? So what that means is we have another floating point addition, right? This is going to be number 7. The last one that we filled in was number 6. And the interesting thing is we can actually schedule it earlier than the floating point addition that we saw before, right? Because we have everything that we need at this stage. Cool. Now, we have a bunch more integer additions. So let's see. This one here, instruction 8, depends on R2 and R4. So let's see. R4 is modified by instruction 3, which is here. And we know that integer instructions have a latency of 2 cycles. So based on this dependency, the earliest that we could schedule this instruction, this instruction 8, would be here, right? Exactly, would be here. And then we look at the other dependency, which is, so we have 8, R2. R2 comes from load with label 6. And that has a latency of 3 cycles. So again, same thing. It would also be available here. So what that tells us is that we can actually schedule the IAD for, so this instruction with index 8, we can schedule it here. Still matching up with the solutions, which is great news. Okay, next one over. Instruction 9, another IAD. This one depends on R5 and R4. So we just modified R4 in the previous instruction, and R5 was last modified by this floating point instruction. Okay, so we're just going to have to take a look at both of those. The latency of floating point adds is 4 cycles. The latency of integer adds is 2 cycles. Okay, so now I want to briefly make notes of the corresponding instruction numbers. So we have 4 and 8. Right, so we have 4 here and 8 here. So 8 has, this one has a latency of 2 cycles, right? And then this 4 has a latency of 4 cycles, right? So that's going to take 1, 2, 3, 4 cycles. So only here does this value from this instruction become available. What that means is I can only schedule this instruction 9 basically at cycle 11. Okay, great. We have a couple more instructions to go. We have instruction 10, which is going to add the values in registers 6 and 2. Those were last modified by instructions 5 and 6. These are both loads, and so we can just take a look at those. 5 and 6. Here, right? So the latest one of them is going to take 3 cycles. So that's going to become available for use here at this stage, right? However, note that we have already, so the instruction that we want to schedule is an integer add, and we've already scheduled an integer add for this point. So what we can do is we can schedule this 10th instruction for right after it, right? Okay. Same logic here. I think you got the idea by now. So we have a dependency on R0 and on R3. R3 was last modified by this instruction 7. R0 was modified by the instruction that comes just before. So let's take a look at this instruction 10. This one has a latency of 2 cycles, right? So this value becomes available here at this point. However, we also need to consider instruction 7. Instruction 7 is a floating point addition. A floating point addition has a latency of 4 cycles. So starting our counting from here, 1, 2, 3, 4, the value becomes available for use here at this stage. Luckily for us, that's the same as the other one. So what that means is that this instruction 11 can be scheduled basically at any point after this checkpoint when both values become available. So we can just schedule our 11 right there. Okay, we've made it to the end. We have one instruction to go, a branch on equals. This branch depends on the values in R0 and R5. R0 is modified by this integer add right before, and R5 comes from a previous integer add. So we care about instructions now 9 and 11. So the latest of which is actually 9, right? So these all have the same latency because they're in the same column. So we can just look at the latest of them. And that's going to take 2 cycles to become available. And so what that means is that this final instruction, the 12th instruction, I can schedule for right after that value becomes available. Okay. Cool. Just for your reference, this is the final solution. This should look almost exactly like mine. And I will highlight one thing, which is the most eagle-eyed among you will have noticed that this table actually has one more instruction than the one that I just filled in. The reason for that is that if you notice, this instruction 8, because nothing else depends on it, can go here, which is the earliest that it can be executed, but there's also no harm in placing it here between 10 and 11, right? That will not affect any later instructions and will also not delay the total time to execute the program, right? Because this, even if this instruction 8 were to start 2 cycles later, it would still be done before, before the program reaches completion. So what the official solutions give us is, ideally, this would be colored in red if this had been printed in color, but basically, note instruction 8 may go in either of the red slots, right? So there were 2 right solutions here. This instruction 8 could either have gone here, where I placed it when I was solving the problem, or here. And, since that doesn't affect the total execution time. Cool. Is everything clear up until now? Okay, awesome. So we only have a couple more questions to go. These ones should be fairly straightforward. So how many total cycles are required to complete the execution of all instructions in the previous question? Ignore pipeline fill overheads and assume that the instruction latencies are the ones given in table 5. So what we need to do now is basically see when the program completes. So when is the latest point at which we complete a memory instruction? All these have the same latency, so I'm just going to look at the very last one, and that one gets issued here and takes 3 cycles, right? Memory takes 3 cycles to complete. What that means is we're going to be done with memory instructions by cycle 6. Let's do the same thing with these integer ones. This takes 2 cycles. So we're going to be done with all integer operations by cycle 12. We do the same thing with the control instructions. The latency for the control instructions is a single cycle. What that means is we're going to be done with these control instructions by cycle 13. Okay, so that's the latest one that we've seen so far. So if we want the total execution, we would use this one. And we just need to check, we know that the float operations take a while. Let's see if that one goes past the branch. And we see that the latency for that is 4 cycles. So whatever starts here takes 1, 2, 3, 4 cycles and is done by cycle 10. So no, the final answer is that we take 13 cycles, right, to be done with the execution of the program. So that's our answer here. What's the total number of cycles? The total number of cycles is 13. And now we want to know what is the utilization of the instruction scheduling slots, computed as the ratio of utilized slots to the total execution slots throughout the execution. I have an important remark to do here, which is that because there is no standard way to measure this kind of utilization, it's very important that you read the question carefully. So in this case, I ask you to give me the utilization as the ratio between the utilized slots and the total slots. But this is not the only way that I could ask this. I could ask between the ratio of utilized slots to the number of VLIW instructions, right? You might see that in different questions on this topic. So always be sure to double check how we want you to calculate the utilization. If it's ambiguous, if you don't know what we mean, be explicit and state your assumptions, right? That's always a good idea. Okay, in this case, we are asked to compute it as the ratio between the utilized slots and the total slots that we had. So how many did we use? We used 4 here, then 1, 2, 3, 4, 5 here, right? Note that here one of the instructions is duplicated. So 4 plus 5 is 9, then plus 1 here is 10, plus 2 here is 12. So there's 12 slots that we used. That's going to be the numerator of the expression, right? And the denominator is going to be how many slots we could have used, okay? And that depends basically on how long the program took to finish. And since we know that the program took 13 cycles to finish, we know basically that there were, for each of these cycles, I have 4 slots that I can use. So the total number of available slots is just 13 times 4, right? It's just literally the number of boxes in this table during the run of the program. So here, this is going to be 12 divided by 13 times 4. Okay, and if you do the math here, this works out to, yeah, basically 3 over 13, which would have been fine, but because I have my cheat sheet here, this is approximately 23.1%. Okay, so in all these VLAW questions, this is a very common question to ask. So it's good that you're comfortable asking for utilizations. Yeah.
So if this cycle some instructions start finishing, we also can count that as
Yeah. Okay, so just to recap the question for anyone who's listening online, the question was, and tell me if I understood correctly, the question was that at this 13th cycle, there's still an instruction executing, right? And the worry was that it would not be done by the 13th cycle. That's a very good point. However, this instruction has a latency of 1 cycle. Okay, so it actually is done by the end of the 13th cycle, right? So be careful with, like, this is, start from 0 and the number of cycles. This is always very tricky, right? But we take up the entirety of 13 cycles to be done, and this one takes 1 cycle to execute, right? This branch run equals. So it is actually done by the 13th cycle. So that's why we use that in the denominator. If, for example, if this had a latency of 2, then you're right. You would have had to use 14 instead of 13. Okay, does that make sense? Okay, cool. Anything else? Okay, then I think we are done for now. All that is left to do is to wish you all the best for the exam and to encourage you to use the forums and all other channels that you already know of to ask for help. Yeah, thanks a lot for attending. Okay, so we have one more question. So I'm just going to stop the screen share here. And okay, and you can take it away, Haosong.
Okay, Joe, thanks. I think I need to have the permission to share my screen. Okay, so can you see my screen?
Yes, we can see it.
Okay, so it's like the PDF and the notes on the right side, right?
Yeah, exactly.
Okay, yeah, cool, thanks. Okay,
Go for
so, okay, thanks. Hello, everyone. In the last question, we're going to solve this cache reverse engineering question. So let's first take a look at the description and extract all the information we need. So first, yeah, this cache is addressed by bytes. We have the following 5 different possible block size, 4 possible associativity, 2 possible cache sizes, and one final thing is the replacement policy, either least recently used or first in, first out. So the only statistics we can get is like the hit rate with like 2 sequences, 2 access sequences, and both of them have 8 different addresses accessed. So the first sequence, it has a hit rate of 1/2. So this means like we have 4 hits. For the second sequence, 3/8, so we have 3 hits. And then the next paragraph is very important. It says that the cache is initially empty before the first sequence, and the 2 sequences are executed back to back. So this means that at the start of the second sequence, it will see the cache as it is in the end of the first sequence. Okay, so the first question is to reverse engineer the block size. To do this, we can, to do this, we can try to group. So first we look at the first sequence. Then we can try to group the addresses in increasing order. 0, 32, 73, 128, 196, 255, 8K, and 16K. So we can immediately observe that no block size smaller than 64 is possible because like they're at least 32 bytes apart. So if like we have a block size of 8, 16, or 32, there would be no hits. And for 64 bytes, we would possibly have this 32 will be a hit. And then we would have like a hit here. So yeah, that's only 2 hits. So now we only have one option left, which is 128 bytes. Let's also verify that. So for that, we would have a hit here, a hit here. So that's like 1, 2, 3, 4 hits. Yeah, so the cache block size would be 128 bytes. Then let's take a look at the second question. So we would like to know the associativity of the cache. So as the description already specifies, at the beginning of the second sequence, it will see the state of the cache as it is in the end of the first sequence. So in the end of the first sequence, we will have the following cache blocks. So starting from now on, I will just use the starting address of a cache block to represent that block. So let's say if I write a 0, this means like bytes 0 to 127, like it's in this like cache block. If I write 1, if I like write 128, then like it's like 128 byte to 255 byte. So yeah, we will be using this notation for simplicity. So at the end of the first sequence, as we can see from our results for the first question, we would have cache line 0, cache line 128, 8K, and 16K. Okay, and then let's take a look at the second sequence. So we can, yeah, and let's also, yes. So this would be the address. And also let's try to know like which set this address could be. So like I put an asterisk on the set because like it might not be the actual like set bit because we don't know like how many set it has yet. But what we do is to divide these address by the we remove all the offset bits from this address because we already know the block size is 128, and what remains will be used to address the sets, so that like this information can help us in determining like what are the possible associativities. So if we divide all of these by 128, we have like 0, 1, this one would be 64, this would be 128. So we can see that this, and this address, they will map to the same set regardless of the cache size and or like associativity, because like they're both like multiples of 2. And then let's take a look at the addresses accessed by the second sequence. So let's see, like let's say S2, sequence 2. The addresses would be, so 127, this would be 0. 4K is 4K. 8K is 8K. 32K is 32K. 196 is 128. And let's also have the set address, 0, 32, 64. This will be 256, 1. And for the next addresses, have 16K. This 128, 0, 0, 512, 4. Okay, so as we can see here, except for like, so we can know for sure that like this access sequencing S2 will not replace the cache block 128 because like, like it's in set 1 and no other sets set asterisk value in sequence 2 could conflicate with it. So we have a guaranteed hit here. So because for S2 we have a total number of 3 hits, then the associativity must make like the number of hits in the rest of like these axes to be 2. And so first let's take a look like associativity of 1. If like it's associativity of 1, then it's like a direct mapped cache. So like all of these axes would conflict, so we would have no hits. So yeah, then we rule out that possibility. Then for the associativity of 2, this means that like in a set we can have like 2 possible slots to put cache blocks. Considering like we only have least recently used or first in first out replacement policy, you can see it very clearly that like because there are like no 2 axes that are like very close to each other that can generate a hit with these 2 policies, associativity of 2 is also like ruled out. Yeah, to save time, like I won't write it out, but I think it's pretty straightforward to see that if you just like try both replacement policies. And then finally for associativity of 8, this means that like for a set we can have like 8 different cache blocks in that set at the same time. So if that is the case, then yes, starting from the first axis, we would hit here, we would miss here, we would hit here, we would miss here. Yeah, like now we and we will hit here. Now we already have like 4 hits in this case, so it exceeds 3. So yeah, we are only left with a possible associativity value of 4-way. Yeah, and then for the third question, sorry, for the replacement policy. So we already know that our cache block is 128 bytes. The associativity is 4-way. Yeah, excuse me. Okay, so then let's enumerate for both ARU and first of case to see which one can generate the desired result that we produce 3 hits in the axis in sequence 2. So to reiterate, at the end or let's say at the beginning of the second sequence, we would have like address 0, address 8K, address 16K in the cache for the for set 0. So for the first axis to 0, it will hit in the cache, and for the second axis to 4K, it will miss, and it will insert another line, this 4K line, into the set. So, and if yeah, and then for the next axis 8K, it will hit. For the next axis 32K, it misses, and it is going to replace a cache line in this set. So if it is the first in, first out policy, it will replace 0. So we end up with the sequence. Then for 128, it's in the first step, so we ignore that. And then, okay, for this 16K, we will hit here. So we have like yet again 4 possible hits. 1, 2, 3, 1, 2, 3, 4. So this contradicts with the number, the hit number of 3. So we only end up with like the ARU policy. And to see it for yourself, you can like just go over this process again, but with the ARU policy. With the ARU policy, when this 32K is inserted into the set, it will replace 16K instead of like 0. So for the next access to 16K, it will miss. So yeah, then we get a final hit number of 3. Okay, so oops. So then for the next question, we want to reverse engineer the size of the cache. In order to do this, we design a following access sequence consisting of 3 addresses. First access like 8K, and then X and Y. So our goal is to come up with the address values of X and Y such that after this sequence, we can know how many bytes are there in our cache. Okay, so the sequence is 8K, X, and then Y. So at the end of the second sequence, we would have the contents in the set as let me think, 0, 8K, 16K, and 4K. Yes. And the, oops, sorry, let me think. Yes. Sorry, this should be this. So yeah, because for the area policy, this would yeah, replace the 0 as we access it here. So in this case, the least the ARU bit would be 32K after we access address 8K in this like probe sequence. So because there are like only two possible sizes, 4K byte or 8K bytes for our cache, and we already know that like our cache is 122 byte block size and 4-way set associative. So this means that for 4K bytes, one set would be 1K large. So all the addresses that are like multiples of 1K, they will hit in the same set. And for 8 kilobyte, all the addresses like that are multiples of 2K, they will hit in the same set. So because like this access sequence brings the ARU bit to this 32K, and the way that we can know whether the size of the cache is 4K or 8K or not is to see if we can replace this least recently used cache line. So in order to do that, we put Y as 32K, such that if Y misses, then we know this then like a previous address X has replaced this 32K address. So in order to do that, we can set like X as X is like an odd number, an odd multiple of 1K. So in this case, if the cache size is 4 kilobyte, then this access of X would replace 36K. And if the cache size is like 8K, then this odd sequence will not replace 32K, and it will go to like another set. So the access of Y to the same address would hit. So by doing this, we can know whether our cache size is 4K or 8K. Yeah, so that solves our last question. So this would be, X would be 2K minus 1. 4K positive integer. Y would be 32K. Yep. Okay, so that solves all the cache problems. Is there any question about this? Okay, yeah, so then I think, yeah, we are done for today's session, and thank you, everyone.